a generalized heat conduction equation. Now, if you want to relax the dimensionality of the problem, you can drop down one by one term. Suppose I am dropping down this term, I am left out with these two terms, heat generation term and this term. So this is going to be a two-dimensional heat conduction equation in Cartesian system, that too with time-dependent solution. If I drop down this term, then this is a one-dimensional heat conduction equation in space and time. Right? So depending upon the dropping down of the terms, you will be actually generating a kind of equation which can be categorized as diffusion equation or parabolic equation, elliptic equation, hyperbolic equation. So here these are some sort of equations being developed based on the dropping down of terms. Suppose you remove this term, it is going to be a steady state solutions for this. Suppose you are going this term, it is the heat conduction equation without heat generation. Now whether this term is to be included or not, it purely depends on the user, on which the user is working on a particular application. Suppose you are working with the nuclear fuel element. So in nuclear fuel element, this term cannot be dropped out because this is the important term which actually distribute the heat in a system. This nuclear rod is basically a cylindrical kind of thing. So this X, Y, Z will be replaced to R, theta and phi. So correctness of the governing differential equation, correctness of the space domain, and the understanding of time domain solution is very important before you jump into any of the numerical simulations. So this is basically known as mathematical formulation of your real world problem. And by dropping down the terms, you are actually trying to convert your three-dimensional domain into two-dimensional domain, transient solutions into steady state solutions, and likewise you are actually converting the kind of, see, we are actually working with the differential equation, and we are come across with two type of equation, that is ordinary differential equation and partial differential equation. So when you are going with the ordinary differential equation, I would say that y is a function of x only. So y being a dependent variable, x being an independent variable, whatever the variation of y with respect to x, that is been taken care of. And when you are representing these things in the differential form, this is truly generating a ordinary differential equation. So in this case, if you drop down all the term, you will be left out with this. So this is going to be a curly square t by curly x square, and this is going to be replaced with the d square t by dx square equal to 0. So this is basically an ordinary differential equation wherein t is a function of x only. Now when you have an ordinary differential equation, the general solution of all the ordinary differential equations are available in the calculus. So you can take care of all this general solution and you solve the problem analytically. But suppose I am adding this one more term into it. So let us say this term. So in this term, I would say that t is a function of x and y. So temperature being a dependent variable, it is depending on x and depending on y. So partially on x, partially on y. So this is going to generate my partial differential equation. Now for partial differential equation, we do not have closed form solutions like what we are having in the ordinary differential equation. And that is why we need to resolve this term. So there are the ways in which you can convert this partial differential equation into ordinary differential equation. One of the ways is what? You can go with the separation of variable methods. So using the separation of variable method, you are actually trying to separate it out, and you are assuming that t of xy is basically a function of xx and yy. This will give you 1d x diffusion equation. This will give you 1d y diffusion equation. You separately solve and get the product of this solution. It will be a kind of solutions for your problem. This is one of the method. Second method is what? You are actually going with the Laplace transformation of the system. So the understanding lies with both the methods what? The nature of partial differential equation is actually going to be converted into ordinary differential equation. And once it has been converted into ordinary differential equation, using the general solution available in the calculus, you can easily solve the problem. Of course, it is a kind of approximation which we are making. So these solutions are going to be approximate solutions, unlike the solution obtained with the real sense of ordinary differential equation. So the understanding of the equation is very, very important before you jump into the numerical simulations for that. Now, when you are going with the separation of variable method or Laplace transform method, and if you are adding these terms over here, then the things will become quite difficult. It will be unnecessarily generating a kind of basis functions and some other functions which are of Sircho kind, and you require some tabular form to see the values of that. So even though solution is available in approximate form, you are not actually sure, and it becomes a very Herculean task to get the solutions of PDE converting into ODE using these methods in an approximate way. So rather, instead of going to get the solution using this method, which are analytical method, people are actually going with the numerical methods. I'm not able to do it now. Okay. Yeah, having understood the governing differential equations and its characteristics, let us discuss with the conditions being imposed, because no equation can be solved without the conditions. So there are as such two types of condition. One is the initial condition, second is the boundary condition. So if I go back to this equation, I would say that t is a function of x, y, and z. So this is going to be a spatial system. T is a function of t. So this is going to be a temporal system. See, if you want to resolve these terms, you require the conditions in the form of boundary. So this is a closed form system. And if you want to resolve this term, you require the boundary in the time domain. So when you specify the condition with respect to space like x, y, z, or r theta z or r theta phi, then these conditions are known as boundary conditions. And when you define the conditions for time, this is known as initial condition. So usually the initial condition is being taken care of in the way like when t equal to 0, the dependent variable t is maybe some value, let us say constant. This constant may be 0 or some other values, or it may be defined in the form of del t by del x equal to something. So these are the initial conditions when you are defining for the time. And when you are defining for x, y, z, or r theta z, or r theta phi, then this is known as boundary condition. So we often encounter the different boundary conditions available to us. So the first boundary condition is known as specified temperature boundary condition. This is also known as Dirichlet condition. So this condition is known as Dirichlet boundary condition. Now in Dirichlet boundary condition, let us say this is one dimensional problem wherein this is one wall, this is second wall. I would say that let us say this is x equal to 0 and this is x equal to L. Usually the boundary conditions are defined for the dependent variable considering the parentheses in the bracket. And you are defining these things. T x equal to L this. In order to remove this repetition of x equal to 0, usually the conditions are defined in this way. And suppose if you are working with the time domain also, so the first is the space domain and second is the time domain, and you are defining these things. Then here. So when you are directly defining the value of temperature, then it is known as Dirichlet condition. So here, suppose this wall is at 150 degrees centigrade and this wall is at 70 degrees centigrade. So I would say that at x equal to 0, t equal to 150. But when time is involved, so I will be writing the condition in this way. Time directly defined as 150 degrees centigrade. Time directly defined as 70 degrees centigrade at x equal to L. So this kind of conditions is known as Dirichlet condition or specified temperature boundary condition. Now second is known as specified heat flux boundary condition. So this is my specified heat flux boundary condition. Now since it is a conduction mode of heat transfer, I will be representing this heat flux as a Fourier's law of heat conduction. That is minus K dt by dx at particular location. So I would say that this is minus K dt by dx at x equal to 0. At this location, I would say that minus Ka dt by dx at x equal to L. This is going to be equal to Q convection. Now convection is been defined as HAS T minus T infinite. So this is going to be a Newton's law of cooling. So if from the surrounding to the solid, if it is entering, then here you have to make the energy balance. So if heat flux is directly given to us, like suppose this is a window like this, and the sun is exposing over here. So you are knowing the value of sun. So this Q0 is the value. So Q0 is the value which is actually entering into it and is moving in this forward direction. So Q0 is equal to minus Ka dt by dx at x equal to 0. When it's going from here, then it is minus K dt by dx at x equal to L. This is going to be equal to QL. So this is directly defined. Here temperature is defined. Here heat flux is defined. And that is why this is known as specified heat flux boundary condition. Now third is the insulated boundary condition. So when some of these surfaces are being insulated in order to prevent the heat loss between the system and surrounding, the surface is getting insulated with the kind of insulations. Insulation in the sense of the value of K is several order less than as compared to metals. So it is because of this value of K, you are actually reducing the heat loss between the two system and surrounding. Now how can I effectively represent this insulation boundary condition? So insulation means what? You are preventing the heat loss from here to here. So I would say that I am putting Q equal to 0. This is from solid to outside. So if I am putting Q equal to 0 minus Ka dt by dx equal to 0. K being a property cannot be 0. A is a geometrical parameter, cannot be 0. So this is the only term which is gradient which is equal to 0. So I would say that dt by dx at x equal to 0 equal to 0. So when you want to represent the insulated boundary condition, it is always been represented in the form of dt by dx. So dt by dx at x equal to 0 is the insulated boundary condition at this location. Now here the temperature is defined. So at x equal to L, temperature is defined as 60 degrees. So this is specified temperature condition. This is the insulated boundary condition. So here, if you are putting this Q as 0, so heat flux is 0, you're putting over here, and that's why you are getting this condition. So this is a third kind of condition which we are actually introducing in the heat transfer problem. Then fourth is the thermal symmetry. So this is my fourth case. Like suppose there are the thermal symmetry. Thermal symmetry means what? See, this is a geometrical similar object. Like if you are tracing a line at the center, and if you see in this part and in this part, if the heat is being transferred in that way, like suppose this is a source, so it will be distributed in this way also, in this way also. But depending upon what is the outside atmosphere you have. So if H is high here and H is lower here, you cannot go with the symmetry situation. But in both the sides, if H is same, then it is a symmetry condition. So symmetricity is being taken care of just by tracing the central line at x equal to 0, and you are putting the insulated condition over here. So I am not going to solve the problem for this domain. I am going to solve the problem only for this domain, considering the fact that the values which I am obtaining, it is a mirror image of these things. So I am actually putting insulation over here, and insulated boundary condition is given by this way. Since it is at L by 2, I would say that del T by del X at X equal to L by 2 equal to 0. So this is a symmetry condition. Now convective boundary condition is what? Like convection, we know that it is represented by the Newton's law of cooling H, that is heat transfer coefficient, and the temperature difference. This is the temperature of medium and this is the temperature of the wall. So H T infinite medium minus T of wall. So T of wall is what at x equal to 0 at time t. So this is going to be a Q convection, which is going to be equal. See, you have to make a balance over here, and from here it is conduction. So this is my conduction. So in order to put this convective boundary condition, Q convection is equal to Q conduction, and by that way you can put up this condition as H1 T infinite 1 minus T0 of T is equal to minus K del T by del X equal to 0. Then this is known to me, this is known to me, this is to be estimated, this is to be estimated. So based on that, you can make use of this boundary condition for your case. Similar is the case over here. Conduction is equal to convection. So minus K dt by dx is equal to H. Now here, fluid is actually heat is transferred from wall to fluid. So this is T wall minus T air. So direction is very important in the case of implementing the boundary conditions for your case. Can you see this? Okay, fine. Then we have a radiative boundary condition. So radiation is being given by the Stephen-Boltzmann law, and it is epsilon sigma a T to the power 4 minus T infinite to the power 4. So basically this is Q radiation is equal to Q conduction. Fine. So similar way you have to replace these things with here. So you need to know that what is my emissivity of this wall, what is the Stephen-Boltzmann constant, what is the surrounding temperature, what is the wall temperature here, and that is going to be equal to conduction mode of heat transfer. Now next is the interface boundary condition. So interface boundary condition is useful when you have more than two materials being in contact with each other. So this is material A with thermal property of K. This is material B with thermal property of Kb. Now interface boundary condition is being defined by two ways. This is known as compatibility condition. Compatibility condition means what? There is a continuity of heat and temperature both. So conduction is equal to conduction. It means that minus K del T by del X at X equal to A. This is equal to minus Kb del T by del X at X equal to B. So this is basically a heat flux balance. And at the same time, I will be assuming that T of A is equal to T of B. So there is a continuity of the solutions right from the left wall to right wall. So in order to define these things, I have to define two conditions. One is the temperature and second is the heat flux. So TA equal to TB is one condition, and minus K dt by dx at this location is equal to minus KB dt by dx at this location. So these two conditions will suffice to define the interface boundary conditions. Now generalized boundary conditions is a mixed condition, or I would say the combined conditions of conduction, convection and radiation. So this actually happen in our analysis of the solar heat flux and some natural circulations in our room. So if you are sitting in this room, it will be governed by the convection mode of heat transfer. Then heat is being transferred from room to the wall, that is going over here, and here it is in the form of radiation, it is in the form of convection. At the same time, sun is actually getting the heat over here. So if you know this condition, I would say that Q is equal to constant. So conduction is going in this way, solar is coming in this way. So accordingly, you have to change the direction. At the same time, I would say that conduction is in this direction, solar is in this direction, and because of that, there is a radiation in this direction. So convection is equal to conduction at this mode. Conduction is equal to radiation and convection at this mode. At the same time, this is to be added into this, so because it is a heat source added to over here. So by that way, you can actually define the generalized boundary conditions for your case. So this is the overall understanding of the spatial and temporal boundary conditions in order to solve this kind of governing equation. So having understood the concepts of a governing differential equation, sorry. I'll be moving with the numerical solution. Now, what does it mean by numerical solution? So let us say y is a function of x. This is a solution. So it means that if you are having the domain at each and every point, this solution is applicable. So this is continuous in nature, right? But now in numerical solutions, what you are doing, you are actually discretizing the domain. With different methods. So you will be actually generating the discrete points. So the solution which obtainable for here, it is no longer be y is equal to fx. It is going to be a function like y is a function of xi. It means that at this particular location of xi, you are generating a solution. Then how close these points, you will be generating solutions and you will be actually getting a curve for them. And that is why the distance between 2 points should be as low as possible in order to improve the accuracy of the solution. So numerical solution in another sense would be known as approximate solution, and analytical solution is known as continuous or exact solution. So there is always the error. So remember one thing, when you are adopting the numerical simulations, error is always there. And in order to get the accuracy of the solution, you should go with the bare minimum error like 10 to the power minus 6 or more. So if you are coming up with the solutions 10 to the power minus 6 or more, then error is minimized in the order of 10 to the power minus 6, and you can comfortably say that my approximate solution is 10 to the power minus 6 correct or accurate as compared to exact solution. Now, since we have to discretize this domain, how can I discretize this domain? So basically there are two approaches. One is the top-down approach, second is the bottom-up approach. You might be knowing this fact, but it is very important to discuss. So in a top-down approach, what has been happening? In a top-down approach, governing differential equations are available to us. Now these governing equations are what? Navier-Stokes equations for the fluid flow, energy equation for the heat transfer and fluid flow, and continuity equation. So 3 momentum equation, 1 energy equation, 1 continuity equation. These 5 equations are always there to solve the laminar flow in a domain. Now when you are going to discretize this domain, these equations are already been represented in a macroscopic form, like this is the equation which is written. Now this temperature is basically a macroscopic property. So what you are doing, you are not going actually a microscale level where the individual molecules have a different properties of temperature. You are summing up and you are pointing out that this is the average property at this location. And that is why all the Navier-Stokes equations, continuity equation, energy equations are represented in the macroscopic properties like U, V, W, pressure, temperature, density. All these are the macroscopic property. So when you are seeing over here, see, this is the region of interest, which is the macroscopic scale. So when you are measuring these things, you are representing that this is my U, V, W, P, rho and T. So you are not actually going in a microscopic way. When you see this region under the microscope, the different particles have different velocities in all these 3 directions. Different particles have different temperatures. Different particles have different pressures. So rather than considering the individual particles interactions, you are actually summing up and trying to find out that this is the macroscopic property, and that is why for the macroscopic scale we are using the Navier-Stokes equations, we are using the continuity equation, we are using the energy equation for the solution. So when you solve this equation, you will be directly given the macroscopic property as U, V, W, P, rho and T. It is as good as you are measuring the temperature, pressure, velocity at a point. So the measurement of temperature, velocity, then pressure at a point is basically a macroscopic property you are measuring. You are not actually going very deeper in the microscopic scale. So measurement with the use of sensor is also a macroscopic property, and solution of this equation is also giving you the macroscopic property. So rather ignoring the individual particle interactions, you are actually measuring the macroscopic property, you are solving the macroscopic property equation. Why is this so? Because we assume that continuum approach is applicable for this macroscopic scale. So with this assumption, we are very comfortable to get the macroscopic property for the solutions of Navier-Stokes equation, continuity equation and the energy equation. So in a top-down approach, what is been over here that we are already having the equations based on the mathematical modeling of the particular applications. These equations are available in a macroscopic propertical way. Then you are going to discretize. And finally, you are getting the quantity which is the solution of macroscopic properties only, like U, V, W, P, rho, T. So you are solving this by discretizing this. Now, when you are adopting the top-down approach, these are the methods available to discretize the domain. Why discretization? Because PD is very complex to solve. You do not have closed form solution. So only way to get the solution is the numerical solution. Now the first and foremost condition for the numerical solution is the discretization of the domain. Now how you discretize? So in order to discretize the domain under the top-down approach, various methods have been introduced. The first method is finite difference method, second is finite volume method, third is finite element method, and fourth is boundary element method. So if you will see here, this is a domain which is to be discretized using the finite difference method. Now the drawback of finite difference method is what? It takes care only the orthogonal coordinates. For irregular geometry, you will be introducing the errors like this. This is the error. So finite difference method is working with the point of intersection of two orthogonal lines, and this is going to be a node point, discrete point developed under the finite difference method. Since it is a point, I do not carry out any mathematical analysis for the equations, and that is why you should have priorly developed dedicated approximate equations for the finite difference method. Now under the finite volume method, this is considered to be a volume. So here in the volume, I am actually considering the centroid of this volume as the node point. Since this is a specified geometry of control volume, it has surface area, it has volume, everything. So what I'm going to do here under the finite volume method, unlike finite difference method where you are having the replacement of the derivatives, in finite volume method you are actually integrating the terms which are of differential nature. So let us say del t by del x. So this is going to be replaced as first of all ti plus 1 minus ti over 2 delta x. So this term is replaced by this in the finite difference method. But here in finite volume method, you are actually trying to consider integration over the control volume. And this is going to be a better approach. It will give us the physical sense of the understanding of our problem, and that is why finite volume method has become very popular. Moreover, for the irregular geometry, this method works well. People have solved so many problems, whether conduction, convection, or radiation, using this finite volume method. Then in finite element method, so we have considered these as a volume for the finite volume, but this is going to be an element. So this is going to be an element and the domain is discretized in this way. So these are the elements. Under finite volume method, these are the volumes. control volumes. So you are directly integrating the differential equations and getting the solutions for that. Getting the discretized equation. Basically, in numerical simulations, what we are doing, when you are adopting this discretization, you are actually changing the governing differential equation into algebraic equation. Algebraic equation is what? You are actually presenting in the matrix form. And once this is the governing differential equation converted into algebraic form of equation, matrix is being generated, and using the suitable matrix inversion technique, you are actually getting the solution. Now, how accurate this algebraic equation, it depends how accurately you have resolved your computational domain for the solution. Again, which method have you adopted for the discretization, it depends on. So if you are going with the finite difference method, you will not get accurate answer. But with the higher order FDM, you can get the answer. Finite volume method works well. It is giving you the accurate solution. Finite element method is one of the methods. We are going to discuss this method in detail for the heat transfer problem. But this is very, very essential to proceed further. What is actually being adopted for the simulations and what is being actually converting in the form of solutions for them. So in any of the methods, whether you adopt the top-down approach or bottom-up approach, you are actually converting governing differential equation into algebraic equation using the suitable discretization technique. So what is the outcome of my finite element method or volume method or difference method or boundary element method? The outcome is the equation. It is not a solution. Remember this thing. The outcome is conversion of differential equation into algebraic equation. So when you convert it into this, you are actually introducing the error. So error analysis is an indispensable part of your analysis when you are adopting the numerical solutions for that. Now, how can we generate this algebraic equation? So according to this method adopted, we are actually discussing this part. In the boundary element method, rather than discretizing the domain, the boundary is actually getting discretized and getting the solutions. See, all these are giving the discretization of the domain. Means actually you are generating the meshing or grids inside the domain. But another method is there which is known as meshless method. So you are generating the points but without creating a mesh. So this method is now becoming popular in the engineering and scientific field, and people are doing a good work using this meshless method. But ultimately the aim is what? The continuous domain is discretized using one of the methods in order to convert governing differential equation into algebraic equation so as to convert it in the form of matrix, and you solve the matrix, you solve this matrix to get the solution. This is the entire philosophy of your numerical simulation. Now what is happening in the bottom-up approach? So in the bottom-up approach, you are starting with this. So you have the individual molecular properties and everything available with you. You want this. Fine. So when you are going from microscopic scale to macroscopic scale, lattice-Boltzmann method is the intermediate scale methods, and this is known as mesoscopic scale. So between the microscopic and macroscopic, LBM is a mesoscopic scale when you are now considering. So suppose you have 5 interactions of the molecules, but you are merging these 5 into one and representing over here, but in every direction you are considering its velocity and everything, and that is why this has been considered as a sandwich between the microscopic scale and macroscopic scale. So for that you are actually moving with the microscopic properties and you are actually getting the macroscopic property as a solutions for that. So this is the overall understanding of top-down approach, bottom-up approach, and numerical simulations. So having understood the concepts of various methods for the discretization, let us start with the one of the methods, that is the finite element method. I think you are already having the idea about this finite element method because this is the third day of your FDP. Even then, I would like to quickly go through the steps involved in the finite element method. The first step is what? Discretization of the computational domain. That is what I discussed right now. Now, what is being happening when you are discretize the computational domain? So your computational domain is, let us say, 1D domain, 2D domain, or 3D domain. So if you are discretizing the 1D domain, you require the element of 1D. If you are discretizing, let us say this, you are solving a problem of heat transfer from one point to another point in a prevailing direction of x. So this is my 1D domain. Fine. Instead of having this, I am going to solve the problem in a plate. So this is going to give me two directions, x and y. So this is a 2D domain. So with the 1D element, I cannot go to solve the 2D problem. Similar way, instead of having this, I am having the cube. And I want to solve the problem in this cube. So this entire thing is considered to be a triangular element. Netherlands. This is known as 2D element. And this is known as 1D element. Fine. So when you are discretizing the computational domain, you have to choose whether this 1D element, 2D element, 3D element based on the space. Now once you are choosing this 1D, 2D or 3D element, then the next step is to develop the element equation. Why element equation? Because you are going to convert the differential equation into algebraic equation. So element equation is very important. This is known as local element equation. So suppose you have two elements. This is element 1, this is element 2. You have separate equations for these elements which are local in nature. Fine. Now when you combine these two local, then it is going to be an assembly of equation, and this is known as global. Fine. Now when you develop this global equation, then depending upon the boundary conditions, you are actually modifying your system. So at the end of this, you are actually in a position to develop the matrix. Once matrix is generated, you can get the solution of this matrix, and you are going with the post processing of your solution. So this is what I am going to discuss with you. Yeah. So when you are discretizing the domain, you will be come across with 1D, 2D and 3D element. So this line is representing the 1D element with two nodes. So this is node number 1 and this is node number 2. But you may increase the number of nodes even in a single element. So this is 1D element with 3 nodes. 2 nodes at the end and 1 node at the center. Now for 2D element, we have two types of element. One is triangular element, second is the quadrilateral element. So corners are representing the nodes. But sometimes what happens for the irregular geometry, instead of having this line, straight line, you are actually making a curve with the approximation. So this is a curved triangular element, this is straight triangular element, this is straight quadrilateral element, this is curved quadrilateral element. Here all the corners are having the node points. Here actually you are increasing the number of nodes. Similar way you are increasing the number of nodes for that. Now in 3D element you have tetrahedral element like this, then curved tetrahedral element with 10 nodes. This is about 4 nodes. This is 3 nodes, 6 nodes, 4 node, 8 nodes. So node is very important, but the moment you increase the node, where would you actually where where can you increase the number of nodes? I'll be discussing in later part. But same element with the more number of nodes, less number of nodes with 2D and 3D. So these are the possible elements we have, and we need to work out with these possible elements. Now, how can we generate the particular equations and global matrix and solutions? I will be discussing that part here. So after selecting the nodes, you discretize the domain. So see, previously the object was without the mesh, but now when you discretize it, it looks like this. So here the entire domain where I want the solution is actually discretized with the help of elements. So these are the elements which you can see. And next is what? And next is what? When you actually get the solutions, you will be getting the solution in this format. So according to the type of traces being generated or some velocity field being generated, the color coding has been given with the magnitude scales of the values. So here this problem is discretized using the FEM model, and this is the result. Now the interpretation of result is very important, and the results accuracy depends on the accuracy of the grid. So when you are going with the solution of any of the problem using any of the method, grid independent study is very important. So there are two things in the numerical simulation. One is grid independent study. So grid independent study will let you know that the number of grids which are suffice to generate the accurate results, and second is the validation. So validation study will let you know that the numerical procedure which is adopted for your solution is correct or not. So when you are validating the result, then you can forecast your results for the rest of the problems. So this is what I am going to discuss in subsequent slide, that how to discuss domain using the elements and get the solutions for that. Yeah. So we may come across with so many problems like solid mechanics, then fluid mechanics, then heat transfer, then diffusions, electrical conduction. So these are the physical phenomena in the practical applications. Now when you convert it into mathematical model, you will be generating the equations. That is a differential equation. So these are the different equations which we are generating for the problem. These equations are associated with the suitable boundary conditions, and then it is going to be approximate using the finite element equations. So when you develop the finite element equation, you will be having the individual element equation which is known as local equation, local element equations, and when you assemble all these equations, this is known as global matrix or global equation. So global equation is actually looking like this, wherein k of u is equal to f. It is basically, I would say that a of x is equal to b. This is a matrix. I would say that this is coefficient matrix, which is always known to me. Fine. This is a column matrix, which is actually the unknown matrix for which the parameters are going to be determined. This is also a column matrix, and this is based on the boundary condition, source term, etc. So all the known boundary conditions, source terms we taken on other side, and it is multiplied with these things. Now, so Ax equal to B. This equation is very familiar in the matrix solutions. Right? Similar way, when you are generating a global matrix. So global matrix looks like this. The notation is slightly different. This is known as stiffness matrix. Stiffness matrix is nothing but the coefficient matrix, which is always known to us. Without this stiffness matrix, I cannot do anything. Then this is the nodal vector. Nodal vector is what? It is an unknown column matrix for which I want to solve the problem. Fine. Say for the example, in solid mechanics, deflection U. So U1, U2, U3, these are the deflections at different points. So these are to be known. So this U is basically a deflection. In fluid mechanics, let us say P. So P is the pressure at different nodes. So P is P1, P2, P3 is to be put up over here. Then thermal conduction, temperature is unknown. So T1, T2, T3 at different nodes will be put up over here. Similar way, diffusion, concentration, indeed mass transfer. So concentration is unknown. C1, C2, C3, it will be put up over here. Similar way for electrical conduction, voltage, V1, V2, V3, you will be putting over here. This Q, B, Q, these are the source term. So source term is anyway to be taken care of under the force vector. Moreover, these boundary conditions are also going to take part in the force. So this is what we are actually understanding the matrix solutions Ax equal to B. We are actually generating the same matrix over here under the finite element method. So in order to understand the problem, I have brought one problem. I have brought one dimensional heat conduction problem, and then we'll discuss more over it. So I am directly moving. So could you see this part? Hello? Could you see this?
Yes,
Hello?
sir.
Hello?
Yes, sir.
So can you see this solve 1D Poisson equation? Is this visible to you, all of you?
Yes, sir. Visible.
Okay, fine. So here I have picked up one problem, and systematically we are going to solve this problem so that you will get the proper understanding of the application of finite element method. Now the problem is what? We need to solve one dimensional Poisson's equation. So Poisson equation is this, basically d square t by dx square plus qg by k equal to 0. This is one dimensional heat generation equation. So this is basically constant or maybe a function of x. So what I'm doing here, this is known to me is a function of x, and I'm keep replacing this as a function x, and this is going to be my source term. Fine. So when you want to solve one dimensional Poisson equation for a 10 centimeter rod, so this rod is actually 10 centimeters, so x equal to 0, and this L is equal to 10 centimeter. Boundary condition imposed are t at x equal to 0, it is 40. So I am knowing that at t x equal to 0, it is 40 here, and t x equal to 10, it is 200. So I would be writing 200 here. So now this is a dirichlet boundary condition. So directly we can apply for this. And as you move from x equal to 0 to x equal to L, since the source term is a function of x, at each and every point my source term is varying, and its magnitude is actually getting increased as you move from 0 to L. So now this equation is very much essential to start with for the finite element method. Now this is a problem of 1D. And as I told you, for 1D, we have line element. Fine. Now the entire domain is divided into 1, 2, 3 and 4 parts. So what I am doing here, actually I am taking a line element of this particular line. Since I want to develop the domain into 4 parts, so what should be the length of my each element? So the length of each element is basically the length of the domain divided by number of domain. So number of domain is what? So length is 10, number of domain to be developed is 4. So this is 2.5. Fine. So each length of the element is 2.5 centimeter. So now I have 1, 2, 3, 4, 5. Now I am going to label it. So how can I label these things? So what is this? This is my element 1. This is my element 2. This is my element 3. This is my element 4. So by that way I have 4 elements. Fine. Now I am going to define the local number and global number. So basically when you are writing a code for your problem, you require the global number, not the local number. Remember this thing. So locally I would say that this is 1, 2. So I would write down E1 of 1, E1 of 2. This is the local number. Fine. But what is my global number? My global number is 1, 2. Fine. Now coming to the E2. So for E2, this is 1, this is 2. So I would write down E21, E22. Fine. So this is my 2, 3. Why? Because this is my point number 3. So in this way, I would say that there is an assembly of second point of element 1 to the first point of element 2. Similar way, second point of element 2 and first point of element 3. So in this way, I will be defining E31, E32. Globally, it is to be defined as point number 3 and 4. And then E41, E45. Globally, it is defined as 4, 5. So now, if I want to represent this, I can say that this is I equal to 1, this is I equal to 2, this is I equal to 3, this is I equal to 4, and this is I equal to 5. Now, this is basically a assembly.
Hemant sir.
Yes.
Your slide is not moving.
No, I am not moving the slide. I am writing on the slide.
Sir, that is also not visible here.
Not visible?
Yes, sir.
1 minute. It is already been said. So I need to Is it visible now?
Sir, the screen is visible, but that is not in a presentation mode.
So, should I stop sharing? Is it visible now? Hello?
No, sir.
Stop presenting. Is it visible?
No, sir. 1 minute, sir. Yes, now visible.
Is it visible?
Yes, sir. Now visible.
Okay. So can you see these points which I have discussed here?
Yes, sir.
Okay. So here I wanted to discuss that this entire problem is to be solved using the finite element method, wherein I am going to make use of 4 elements, and since looking to the 1D nature, I am going to introduce line element for that. Now line element is what? This is the line element which is having the local number as 1 2 everywhere. So E1 of 1, E1 of 2, this will give me the global number as 1 2. Then E21, E22, 2 3, E31, E32, 3 4, and E41, E45 is 4 5. So when you assemble all these things, you will be coming with the global number, and this is going to be solved in the problem. So here I equal to 1, I equal to 2, I equal to 3, I equal to 4, and I equal to 5, where I is the general indices. Fine. Now in order to solve this problem, what I am going to do here, that I will be taking first element, let us say 1 2, taking a reference here, I'll be defining that this is x1, this is x2, and let us say this is h, which is x2 minus x1. So globally I am defining this is x2, this is x1, and difference between these two is x2 minus x1. Now I am going to solve this problem. D square t by dx square is equal to minus fx. So I would say that I will be developing in general first, and then I will be replacing that part. So if u is a function of x, then this is going to be a dependent variable, and this is going to be an independent variable. Fine. Now we need to assume the solution for this particular element. So first we will be starting with the u bar. See, u is a exact solution, while u bar is an approximate solution. Fine. So I am using this u bar as u0 plus u1 of u. This is going to be a polynomial equation. Fine. Now for this point number 1 and 2, I am going to generate this equation u1 as u0 plus a1, this is x, a1 x1, and u2 is equal to a0 plus a1 x2. Now this is my equation number 1, this is my equation number 2. Fine. What is unknown to me? A0, A1 is unknown to me. So what I am going to do here, I am going to make use of Cramer's rule. What will I do? I will be multiplying this with x2 and this with x1. And by that way, using the suitable summation techniques, I will be finding that my A0 would be u1 x2 minus u2 x1 divided by x2 minus x1, and by that way I am going to develop a1 is basically u2 minus u1 divided by x2 minus x1. Now once I know this u0 and u1, I am going to put up over here for u1 and u2. So when I am putting these things in the u1 and u2, see, u bar is basically a0 plus a1 into x. Now I am putting the value of a0 and a1. So what is my u bar? So this is u1 x2 minus u2 x1 divided by x2 minus x1 plus u2 minus u1 divided by x2 minus x1 into x. Now when you properly arrange these terms, I am able to get u bar is n1 u1 plus n2 u2. This is my approximate solution, wherein I am able to find out u1 and u2 for this node. u1 is this, u2 is this, because u is a dependent variable. If you replace this u with t, then this is going to be t bar is equal to n1 t1 plus n2 t2. Clear? Now what is n1? So n1 is defined as x2 minus x divided by x2 minus x1. What is n2? n2 is equal to x minus x1 divided by x2 minus x1. See, these n1 and n2 are known as interpolation functions. Clear? Now here I am going to discuss the part as, suppose instead of having the 4 elements, you want to complete the problem in 2 elements. But when you convert it into 2 elements, the number of nodes of each element should be increased. So in that sense, suppose I am converting the entire domain into 2 parts, like 1, 2 and 3. This is element 1, this is element 2, and with this kind of assumption, this will give me the error-free solution. So if you want to improve the accuracy of the solution with less number of elements, the approximation order should be increased for each element. Here it is a linear polynomial equation, but when you are reducing the number of elements in the domain, you increase the approximation of the individual element in the domain, so that you can get the accurate solutions for that. So now what I'm going to assume, u bar is equal to a0 plus a1x plus a2x square. Now for that, what I'm going to do here, that instead of having 1, 2, I will be introducing the third point here. So this is basically a quadratic approximation. And as you know that when you increase the approximation order, you will improve the accuracy. So anyway, linear equation is less accurate as compared to quadratic equation. Fine. So when you are going with the simplistic approximation, you increase the number of elements in the domain, but this will increase the compressal time. So if you want to reduce the number of elements in the domain, you reduce it. Instead of having 4 elements, you reduce it into 2 elements. But each element should have higher order approximation. Did you get my point? There are 2 ways through which you can get the accuracy of the solution. More number of element with this simple approximation, or less number of element with the higher approximation. These are the ways in which you can improve upon the accuracy of the solution. Is this okay? Now here our target is to find out a0, a1 and a2. So again, when you solve this in the form of x2, x1, x3, then you will be getting the approximation as n1 u1 plus n2 u2 plus n3 u3. So this is the approximate solution of individual element with quadratic approximation, and this is the approximation solution of line element with the linear approximation. So this is to be understood that how to get n1, n2 and n3. Fine. Now in the next stage, I am going to discuss see in previous case I have defined n1 is equal to x2 minus x, x2 minus x1, and n2 is equal to x minus x1, x2 minus x1. So here I am going to rewrite the same thing. N1 is equal to x2 minus x, x2 minus x1, N2 is equal to x minus x1 divided by x2 minus x1. So now here, if I want to find the value of n1 and n2, I want to find out the value of n1 and n2 at x equal to x1 and n1 and n2 at x equal to x2. So when I am putting x equal to x1, the value of n1 is 1. So here I am getting n1 1 and n2 as 0. Similar way, when I am putting the value of x is equal to x2, I am getting n1 equal to 0 and n2 equal to 1. So if I plot it like this, this is the magnitude n1, this is the magnitude n2. So n2 is equal to 1 when x equal to x2 and n1 is equal to 1 when x equal to x1. Please keep this in your mind. Now, since you are working with the derivations, so I must go with the derivation of this. So what is my dn1 by dx? So dn1 by dx would be minus 1 over x2 minus x1. So this is basically 1 over x1 minus x2. What is my dn2 by dx? So dn2 by dx is directly coming as 1 over x2 minus x1. Fine. Now since we have already defined that u is equal to, that is u bar is equal to n1 x1, sorry, n1 u1 plus n2 u2. Now what is my du by dx? So this is basically dn1 by dx into u1 plus dn2 by dx into u2. So from this I am able to find out u2 minus u1 divided by x2 minus x1. Now if you integrate it from x1 to x2, that is u bar into dx. So this is basically what happening over here, x1 to x2, u bar is replaced to what? n1 u1 plus n2 u2 into dx. So finally this will give me the answer as 1/2 x2 minus x1 into u. So this is sort of differentiation and integration of u bar n1 and n2 for my problem. Now how do I make use of these things for my problem? So once I am developing these things, what is my basic equation? D square t by dx square is equal to minus fx. If I am solving this, I will be getting the exact solution. It means that if t calculated is exact in nature, then this is going to be 0. Fine. But with this discussion over the finite element, what I am going to do in this equation, I am going to replace this t as t bar, which is maybe n1 u1 plus n2 u2 as linear approximation. Fine. Or maybe n1 u1 plus n2 u2 plus n3 u3 as quadratic approximation. Is this okay? So if you are going with this equation, you require more number of elements to get the solution accuracy. If you are going with this approximation, you require less number of elements for the accuracy. This is the only thing which I wanted to discuss with you in this case. Now, this is my governing differential equation, which will give me the exact solution when t is exact in nature. In finite element method, what I am going to do, I am going to replace this t with the approximation as t bar. So I am going to rewrite approximate governing differential equation. So this is d square t bar by dx square plus fx equal to what now? See, t is replaced to t bar, and as we discussed, this is the approximation. So approximation will never generate the exact solution. So it means that if I am replacing t to t bar, I am generating the error. That error cannot be 0. That error can be in the range of 10 to the power minus 6 or minus 7, but this cannot be 0. So this error is known as residue. So when I'm replacing this t to t bar, it is not equal to 0 now. It is going to be equal to residue. Are you getting my point? All of you, please. Hello. Hello. Am I audible? Hello.
Yes, sir. Audible.
And have you seen this approximate equation that is represented as R?
Yes, sir.
Okay, fine, fine. So the understanding is what? The understanding is the governing differential equation, whatever it may be, the dependent variable is to be approximated with the local equation. These local equations are being generated based on the polynomial approximation, maybe order of 1, this order of 1, order of 2, this order of 2, then cubic, order of 3, then up to n. So depending upon the order of approximation which you are providing for the exact solution, you are going to generate the error, and this error is known as residue. Fine. Now, what is my target? My target is to minimize this residue to 0. It cannot be equal to 0. Remember one thing. This can be minimized to be equal to 0. So, in order to tune this, I am going to use method of weighted residue. This is known as method of weighted residue. Now, what is method of weighted residue? See, the objective of method of weighted residue is to minimize the residue tending to 0. This is the sole objective of this method. How can I find this? So I will be integrating the residue multiplied with the weightage function over the domain and trying to put equal to 0. Is this okay? And for I is equal to 1, 2, 3 up to m. So residue is going to be multiplied with the weightage function associated with that, and it is going to be integrated over the domain. Since we are working with the one dimensional domain, this is going to be equal to x1 to x2 and this is dx. Is this okay? Now, for this, what is my r? My r is this. So I am going to integrate. See, the domain is what? One dimensional. So this is x1 to x2. So this is x1 to x2. Now r is replaced to what? D square t bar by dx square plus fx into wi into dx. This is going to be equal to 0. Now, the main problem lies in the understanding of weightage functions. But we are already having these n1, n2. See, what are these n1, n2? These are known as interpolation functions. And these values lies in between 0 to 1. So when you summed up this omega I, this should be equal to 1. So when you replace this omega I with ni, then this method is known as Galerkin's method. So overall, the entire method is known as Galerkin's method of weighted residue. Fine. So now what I'm going to do here, that I'm going to replace this wi with ni. So here x1 to x2 d square t bar by dx square plus fx into ni into dx equal to 0. Now I am going to separate it out here. So I am going to write down x1 to x2 d square t bar by dx square into ni. This is ni of x dx. This is going to equal to what? Minus x1 to x2 fx ni of x into dx. Now usually this is u into dv. How it is u into dv? Because this d square t by dx square can be written. This is x1 to x2 nix d by dx of dt bar by dx into dx. Fine. So I will be using the product integration rule. So what is this product integration rule? Suggests that a to b u dv is equal to what? U v of a to b minus integration from a to b v into d. This is the product rule available to me, and now I am going to see that what is my u? So I am considering ni of x is my u, and what is my v? So v can be actually d square t by dx square into dx. That is my v. So if you are taking dv, this is dt by dx, right? So now, based on that, uh, for this, let it be like equation number 1 here. Now I am going to focus on this. So when you are writing these things like x1 to x2, ni of x d square t by dx square into dx is t bar. Using this product rule, I can write down u, that is ni of x, v, that is dt bar by dx at x1 to x2 minus integration from x1 to x2. Now this is v. So v is again dt bar by dx, then du. So du is what? D by dx. So d ni by dx into dx. And I equal to what? 1 and 2, because I have two elements. I equal to 1 and 2. Now please focus on this part. So from this, suppose if I am putting n I equal to 1, so here. So what is this equation? N1 of x dt by dx at x1 to x2. This is going to be equal to what? N1 of x2 dt bar x2 by dx minus n1 of x1 dt bar x1 by dx. Now n1 of x2. So n1 of x2 is 0 and n1 of x1. So n1 of x1 is 1. So I would say that this term gets 0. So I am left out with n1x dt by dx at x1 to x2 would be. Now moreover, n1 of x1. So what is my n1? N1 of x1 is x2 minus x1 over x2 minus x1. This is 1. So I can say that this is minus dt bar x1 over dx. So now n1 from here, if I am putting I is equal to 1, so this is n1x of dt bar by dx x1 to x2. So I am getting this value. Similar way, if I am putting I is equal to 2, so this is n2x. So n2x dt by dx x1 to x2 is equal to n2x2. So n2x2 is 1 and n2x1 is 0. So I can directly write down n2x dt by dx x1 to x2 is dt bar x2 over dx. Fine. Now please see this equation number 1 here. D square t by dx square nix into dx. So d square t by dx square nix into dx is this. Now I am putting I is equal to 1 and 2. So for separate two equations I have generated for I equal to 1 and I equal to 2. This is going to be discussed now. So in our next case, I am going to discuss what is happening with this. So if I am writing x1 to x2 dt bar by dx dn1 by dx into dx, then this is going to be minus dt bar x1 by dx plus integration of x1 to x2 f of x n1 of x into dx. See, this is from this understanding that we have developed this equation. So this is going to be appear here, x1 to x2 fx n1x into dx. So when I'm writing this equation for 1, I'm putting I is equal to 1. So d square ty by dx square n1x into dx is equal to this. Okay, and here this is going to be replaced with this. So for I equal to 1, this n1 of x d square t by dx square will be written as what? N1 of x dt bar by dx this, and this is going to be minus dt bar x1 by dx, and this term will be as it is appear over there, and that is why I am going to get this equation for I equal to 1. This is for I equal to 1. Similar way, I can write down this equation dt bar by dx dn2 by dx of dx equal to what? dt bar x2 by dx plus x1 to x2 fx n2x into dx. This is for I equal to 2. So remember one thing, that we are still on this first element where this is point number 1, this is point number 2. I would be considering this is I equal to 1 and I equal to 2. So now I have developed two equations for I equal to 1 and I equal to 2. So these are the two equations which I have developed for my case. Clear? Now I want to do something on it. So x1 to x2 dt bar by dx into dn1 by dx into dx. So let us go back. I did something over here, that dn1 by dx is 1 over x1 minus x2. dn2 by dx is 1 over x2 minus x1. So I'll be making use of these things, dn1 by dx and dt bar by dx. So what is my dt bar by dx? So du by dx is represented as u2 minus u1 over x2 minus x1. Fine. So du by dx is u2 minus u1 by x2 minus x1. dn1 by dx is 1 over x1 minus x2. So if I'm replacing this thing, this is minus u1 plus u2 by x2 minus x1 whole square. So from this, I can write down t1 minus t2 divided by x1 minus x2.
Thank you.
Fine. And this is x1 to x2 dt bar by dx dn2 by dx into dx can be represented as t2 minus t1 divided by x1 minus x2. Now I am going to replace this term with this term with this. Okay, so this term is represented as T1 minus T2 divided by x1 minus x2 here. This is going to be equal to minus dt bar by dx plus this term. And for I equal to 2, T2 minus T1, x1 minus x2 is put up over here. This is going to be equal to this. So I have two equations now. These two equations can be suitably casted in the matrix formulation. So if I am going to suitably cast this in the matrix formulation, then I am going to generate the matrix as 1 over x2 minus x1, 1 minus 1 minus 1 1, T1 T2. This is going to be equal to what? Minus dt bar x1 by dx and this is dt bar x2 by dx plus, again is a column matrix, so integration of x1 to x2 fx into n1x dx, integration of x1 to x2 fx into n2x dx. So this equation A, this equation is known as 1D line element equation using first order linear approximation. This is okay. So now I am going to generate the equation for our case. Now for our case, fx is given as 10. So I am going to find out these things. This is x1 to x2, so this is 0 to 2.5. fx is given as 10. And what is my n1x? So where is my n1? Yeah, n1 is equal to x2 minus x divided by x2 minus x1. So here x2 is 2.5 minus x divided by 2.5 into dx. So from this I will be getting the answer as 12.5. Similar way I am going to find out for this. So again 0 to 2.5, fx is 10, and what is my n2x? So n2 is x minus x1 divided by x2 minus x1. So here it is x minus x1 is 0 divided by 2.5 into dx. So again this comes out as 12.5. Clear? Now what is this x2 minus x1? 2.5. So from equation A, 1 over 2.5, 1 minus 1 minus 1 1, T1 T2 is equal to what? Minus dt by dx at x1 plus dt by dx at x2 plus 2 dt by dx at x1 plus dt by dx at x2 plus 2 dt by dx at x2 plus 2 dt by dx at x2 plus 2 dt by dx at x1 plus 2 dt by dx at x2 plus 2 dt by dx at x2 plus 2 dt by dx at x2 plus 2 dt by dx at x1 plus 2 dt by dx at x2 plus 2 dt by dx at x1 plus 2 dt by dx at x2 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 plus 2 dt by 12.5, 12.5. So I am going to generate the equation. This is 10 by 25. So 2 by 5, 0.4. So now I am going to generate the first equation. 0.4 T1 minus 0.4 T2 equal to minus dt by dx of x1 plus 12.5. This is my equation number 1. Similar way, 0.4 T1, this is minus, plus 0.4 T2 is equal to dt by dx of x2 plus 12.5. This is equation number 2. Now, the beauty of this is equation is what? Since the element is same, the length is same, so it is a uniform grid. If the length is same, element is same, approximation is same, what we are going to do here, that this is 1 point, this is 2 point, this is 3 point, this is 4 point. So element 1, element 2, element 3. Now these two equations are for this one. So I am putting these as 1, 2, then 1, 2, then 1, 2, then 1, 2. And globally the points are 1, 2, 3, 4, 5. So I would say that this is I equal to 1, I equal to 2, I equal to 3, I equal to 4, and I equal to 5. Now these two equations are for this particular element. Since the length is same for all the elements, the approximation is same for all the elements, I will be simply changing the values for my case. So first two equation would be like this: 0.4 T1 minus 0.4 T2 equal to minus dt by dx of x1 plus 12.5. This will remain same. Now I have overlapping of equation number 2 with the equation number 1 of second element. So what is my equation number 2? So this is minus 0.4 T1 plus 0.4 T2 is equal to dt by dx of x2 plus 12.5. This is my equation number 2. Now I am going to write down the equation number 3 for line element 1. Sorry, line element 2. So this is going to be like this equation. So 0.4. Now this 1 is equal to 2. So I would say that this is 0.4 T2. Okay, let me write down in this way: 0.4 T1 0.4 T1 minus 0.4 T2 is equal to minus dt by dx of x2 again. Fine. Plus 12.5. This is my third equation. Now, what is to be taken care of? See, this will remain as it is. Now based on these two, what I'm going to do, see, locally the point is 2. So wherever third equation 1 and second equation 2. So this and this will be same. Fine. So I am going to write down based on this 0.4 T1. Since these two are same, this is going to be what? 0.8 times T2. And 2 of 11, 2 will become 3. So minus 0.4 T3 equal to what? So this is dt by dx x2. This is minus dt by dx x2. This gets cancelled out and these two will be added. So this is 25. So this is my global equation. So for point number 1, I equal to 1. For I equal to 1, what is my equation? My equation is 0.4 T1 minus 0.4 T2 is equal to minus dt by dx of x1 plus 12.5. This is my equation number 1 in a global matrix. For I equal to 2, this is the I equal to 2 for local matrix. This is I equal to 1 for local matrix. But assembling these two, I will be generating this equation. So for I equal to 2, the equation to be solved is for I equal to 2, and that is this equation. Minus 4 T1 plus 0.8 T2 minus, minus 0.4 T3 equal to 25. This is my second equation. So if I am going to represent the second equation, so second equation of this element means this, wherein this is x3, and first equation of next element. So this equation where it is x3. Fine. So when you assemble these things, finally I am going to generate the matrix which is my 5 by 5 matrix. So one, 2, 3, 4, and 5. Now I am going to write down, see what are my 5 unknowns: T1, T2, T3, T4, and T5. These are my 5 unknowns, where T1 is known, T2, T5 is known. So based on that, we will be calculating these things. Fine. Now in the first equation, this is 0.4 T1 minus 0.4 T2. For T3, T4 and T5 it is 0. And this is going to be equal to what now? 0.4 T1 minus 0.4 T2 is equal to minus dt by dx of x1 plus 12.5. So I am going to write down minus dt by dx of x1 plus 12.5. Now what is my second equation? Minus 4.4 T1 plus 0.8 T2 minus 0.4 T3 is equal to 25. So now I am going to write down this as minus 0.4 T1 plus 0.8 T2 minus 0.4 T3 0 0. This is going to be 25. So all these will be 25 in between, and these 3 will be 0, then these 2 will be 0, then this is going to be 0, this is going to be minus 0.4, 0.8 minus 0.4, 0, minus 0.4, 0.8 minus 0.4, this is going to be minus 0.4, and this is plus 0.4. This is dt by dx of x5 plus 12.5. Now when you see this problem, then if you will see, this is main diagonal, this is upper diagonal, this is lower diagonal. So basically this is going to be a tri-diagonal matrix, and Thomas algorithm will give you tri-diagonal matrix algorithm. See, this is completed in 2 steps. One is forward elimination, and second part is backward substitution. This is going to be a direct method, so no need to go for iteration, so no iteration. But if you want the iteration, then another method is Gauss-Seidel iterative method, where you have to assume the T2, T3 and T4. Since T1 and T5 are known to me, so I will be assuming T2, T3 and T4, and then taking the iterations, I will be solving the problem. See, beauty of finite element method is what? You can directly get the heat flux associated at the van walls. So let us say this is the problem to be solved for our case. This is x equal to x0, or I would say x1 at I equal to 1, where temperature is defined as 40 degrees centigrade. This is x equal to x5 at I equal to 5, where temperature associated is 200. So in this case, I would say that T1 is equal to 40, T5 is equal to 200. Now in order to find out with the other methods the heat flux at this location, so I have to go with minus Ka dt by dx, that is equal to Q. But since this method directly take care of these things, So minus dt by dx of x1. What is this? At this location. Multiplied with k and a. Here we assume k and a is taken out. So there is no effect of k and a here. But if there is effect of k and a, this is going to be multiplied with k and a over here. So here you can directly take care of gradient. So apart from T2, T3, T4, this T2, T3, T4, you will be finding dt by dx of x1 and dt by dx of xy. Multiplying with k and a in both the cases, you are able to find out what is the heat flux going inside and going out of this box. This is the way in which you can solve the problem for your case. Now, suppose I want to introduce k and a both things over here. So where would I introduce this thing? So this is going to be introduced here. This d by dx of dt by dx. So instead of having these things here, I will be defining x1 to x2 d by dx of ka dt by dx plus fx, then ni dx equal to 0. So now ka, suppose k is constant and a is constant, so everywhere k comes out from here. So your final equation would become what? Here it will be ka. Suppose a is vary, like the problem which I am going to discuss here for the heat transfer in a see, the problem which we have discussed is this, which has got uniform cross-sectional area. I would say that AC is equal to constant. But we will be finding the problem like this, where we do not have uniform cross-sectional area. And you want to solve this problem taking the linear element 1, 2, 3, 4, 5. Now, I am going to define, since it is a 1D problem, I am going to define this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7. Please bear with me because it is at the center. Now, if you are considering the domain here, this is my point 1, point 2, point 3. So when you compare the area at point 1 and point 2 and point 3, these are different because area is actually reducing. So here I would say that area is a function of x, and that is ai. This is I minus ai minus ai plus 1 divided by xi plus 1 minus xi into, I want to find out the area at this location, so this is xi plus 1. So this is going to be replaced by this way and put up over here. So suppose area is constant, you can take it out. K is constant, you can take it out and multiply these things and you can get the solutions for that. But suppose area is not constant. So this is d by dx of k. K is taken out. So area into dt by dx. So when you are doing this u into dv approximation over here, at that time you need to take care of it. So this is a way in which you can take care of the problem like this. Now when you have a problem of composite material. Fine. And for this problem you want to solve. So what will you do here? That this is the first element, this is the second element. So see, you have to take care of the temperature of first element would be equal to temperature of second element at this location, and temperature of second element, temperature of first point of second element would be equal to temperature of second point of first element, and it will be taken care of over here. Fine. At the same time, the heat flux of this will be equal to heat flux of this. So you can divide it into two elements for more accuracy, or with this single element with higher approximation. So in order to improve the accuracy of the solution, what you need to do, you can take care of more number of elements with simple approximation, or you can take minimum elements with the higher approximation. So this is one of the problem wherein you can take care of this. Fine. The another problem is what? This is a pin-fin kind of problem where the differential equation entirely is different. D square t by dx square minus m square t minus t infinite equal to 0. So when you develop your equation, you please take care of these things, because we are replacing this t. So what will you do here? That you replace it with the theta. Fine. So this t minus t infinite is theta. So from that you can define d square theta by dx square minus m square theta equal to 0. Fine. Now you replace this theta to theta bar, and accordingly arrange the equation for your node points. So likewise, you can solve so many problems using this finite element approach for the heat transfer cases. So I will stop presenting. Yeah. So with this, I would like to end up my lecture. And if you have any doubt, you can ask me. Hello.
Hello, good
Yeah.
afternoon, sir. This is Rahul Patil.
Yeah.
I would like to ask one question that whatever the equations were governing equations we are considering for thermal bodies, so it will be applicable for convection as well. Convection heat transfer. Can we solve the problems of convection and radiation
Yeah.
also?
Finite element method is a discretization technique. So here, please keep this in your mind that whichever technique you have, whether finite difference method, element method, or volume method, you have to mathematically apply over the governing equation,
Yeah.
because these are the top-down methods or top-down approach method wherein the equation is required to be present there. So if you are talking about the Navier-Stokes equation, yeah, you can solve the problem using FEM of all those Navier-Stokes solutions also.
Just we require the differential equation and boundary conditions for it.
Boundary condition is different. See, boundary condition can be convection, but you are talking about the problem itself is convective problem, or boundary condition is convection.
Boundary condition is convection.
So if boundary condition is convective, then here, if you will see, one minute. Can you see this?
Yes, sir. Blank screen is there.
Blank screen. Can you see this now?
Yes, sir.
Yes, sir, visible.
Yeah.
Yes.
So what I discuss here, that in this problem the heuristic boundary condition was imposed, like t is equal to 40 and t is equal to 20.
Yes.
So when we solve the problem, we develop the equation boundaries at the first node and last node. Clear?
Yes. Yes, sir.
Now dt by dx is x1. Suppose t1 is known to me, so I am taking t1 over here. t5 is known to me, I am taking t5 over here. So my entire matrix would be reduced to t2, t3 and t4,
Yes, sir.
and this will be clubbed over here. Now suppose t1 is given at the x equal to x1 and convection is given at x equal to xy. So when convection is given at x equal to xy, this t5 is an unknown point to me.
Right.
So
sir.
when it's an unknown point to me, I have to take care of this convection over here.
So we need to convert the convection formula. Means
Yeah,
we
Q
have to apply-
conduction is equal to Q convection. See,
Right. Right.
what you need to do here at node number 5, say at node number 5 here. So Q conduction is equal to Q convection. So
Mhm.
this is minus Ka dt by dx at x equal to 5 is equal to HAS t minus t infinite at x equal to 5. See, area gets cancelled out.
Yes.
So what is my dt by dx at x equal to 5? This is h by k t infinite minus t5.
Yes.
Is this okay?
Yes.
So this dt by dx at x equal to 5 is going to be replaced with this, wherein you can incorporate what is the value of h and what is the value of k. And t5
Yes.
being unknown, you can keep it over here. So this equation is going to be replaced with this one, taking t5 over here. So when you are developing the fifth equation, on this side, it will be a presence of h into t infinite by k.
Yes. Yes.
And this coefficient is getting changed. Is this okay?
Yes, sir. Yes, sir.
Okay. Similar is the case of radiation. Suppose Q conduction is equal to Q convection plus Q radiation. So this is HAS T minus T infinite, and this is epsilon sigma T to the power 4 minus T infinite to the power 4. Fine?
Yes, sir.
So this is HAS T minus T infinite plus epsilon sigma T square minus T infinite square t square plus t infinite square. So this is HAS t minus t infinite plus epsilon sigma t minus t infinite t plus t infinite t square plus t infinite square. Now I am taking t minus t infinite common. So t minus t infinite I am taking common. What I am left out with what? HAS plus epsilon sigma t plus t infinite t square plus t infinite square. I am considering this as HR. So in this case, minus Ka, K is taken out because area is same. So this is area. So AS will be cancelled out. So here minus K dt by dx at x equal to x5 is equal to HR
Into
t minus t infinite. If you take this k over here, so dt by dx at x equal to 5 is basically now minus hr by k t minus t infinite. And what is this hr? hr is from here because it is known to me. I am assuming that hr is known to me. hr is known as combined convective radiative heat transfer coefficient. So when there is a convection and radiation both, the same equation will be carried forward. That is what you are assuming here. But this H is replaced to HR only.
Yes.
Suppose you have a insulated boundary condition here. So in this case, minus Ka dt by dx equal to 0. Fine.
Right.
So I would say that dt by dx at x equal to xy equal to 0. So this is going to be 0. But this is unknown. Are you getting my point?
Yes, sir.
When temperature is known, then this is known to me. But when temperature is unknown and gradient is defined, then dt by dx is to be 0. So in this case, I will be putting this is 0, but this is unknown. Why unknown? Because this is going to be updated with the equation. So anyway, temperature is there, but gradient is 0 because of the insulated boundary condition. So I will be putting this is equal to 0.
Yes.
Any other doubt? And heat generation is already taken care of as Fx. I have considered Fx is equal to 10. But suppose you are considering Fx is equal to Ax square or maybe 9x square. So according to the value of x, your value will be changed. So in our case, x equal to 0, x equal to 2.5, x equal to 5, x equal to 7.5, and x equal to 10. So when I am putting x1, so x1 is 0, x2 is 2.5, x3 is 5, x4 is 7.5, and x5 is 10. So you have to suitably model the value of x of I, because it is the array. So array is to be defined by this way, x of I. If it is a constant, no need to define array. But if it is variable, then you need to define this x of I. Or in method, you are defining in this way. Is this okay?
Any other questions from the participants? Please unmute yourself, please. I think, sir, questions from the participants are not there. On behalf of FDP team and Mechanical Engineering Department, Government Engineering College, Bharuch, I thank you so much, sir. The session was very interesting. The way you started with basic ODE, PD equations for conduction heat transfer and then proceeding towards approach for FEM method was very much easy to understand. Thank you so much, sir, for your valuable time, and we hope to have you again. Thank you, sir.
Yeah, thank you very much for giving this opportunity, and I am happy with the presence of these participants. And if you have any doubt, you can contact me. You can search the website if you want to. If you want to do something with me, so you can go through the website. It is available on my website. The details are available on the website. So thank you very
Yes,
much.
sir.
Should I discard
Yes,
now?
thank you. Yes, sir.
Okay, okay, fine.
Yeah, thank you. A very good afternoon to all. Shall we start, Modi sir?
Yes, madam.
Hello.
Okay. Yeah.
Madam, sir, welcome.
Thank you so much, sir. Thank you. Am I audible?
Yes, sir.
Yes,
Okay,
sir.
good. Thank you. Thank you very
Uh,
much.
yeah, welcome, Dr. Pathan, sir. Dr. Pathan is presently working as an associate professor in mechanical engineering department at LD Engineering College, Ahmedabad. He graduated in the year 1994 from Government Engineering College, Modasa. He has been in government service for the last 23 years after working for about 4 years in the industry after graduation. He pursued his MTech from IIT Delhi in 2007 with specialization in design of mechanical equipment, and he was conferred upon the doctorate degree by the IIT Bombay with his research domain vibroacoustics. He has been working with number of CAD software for the dynamic design and noise and vibration control for mechanical equipment. He has been a part of research committee and he is one of the 4 members of the committee at LD College of Engineering, Ahmedabad. Many industries have approached the institute for his consultancy work and he has successfully completed the projects. He has taught more than 38 subjects at UG and PG level, published more than 40 papers and guided 12 PG students. Besides, his main area of interest is noise and vibration control, and he has been teaching finite element analysis and optimization, computational methods, and allied subjects at UG and PG level. He is also a DPC member of Gujarat Technological University doctoral program. Sir, we are very much privileged to have you, and I uh, invite you to start with the session, sir. Hello. Hello? Hello? Pathan sir is there. Dr. Pathan.
તમે જે વ્યક્તિને કોલ કરી રહ્યા છો તે જવાબ આપી પછીથી
પઠાણ સાહેબનો અવાજ નહીં આવતો.
ઓકે છે.
Yes, sir.
Yeah. So should I start?
Yes, sir.
Okay, thank you so much. Thank you. Is my screen visible, sir?
Yes, sir.
Yes, sir. Visible, sir.
Good afternoon, everybody. Thank you very much for giving a very nice introduction. And I'm very much thankful to all the organizers of this training program for inviting me to deliver an expert talk. Today I'm going to present on selection of finite element types and meshing fundamentals of finite element analysis method. Before starting the session, I would like to know about the participants. How many participants are there in all such in the training program? And Modi sir.
Sir, there are 200 registered participants, but amongst that, around 125 are joining the training program.
Okay. And are they from the government, from the institutes, faculty members?
Sir, they are from institutes of AICT approved institutes from all over India.
Okay. And what about domain? Are they from mechanical engineering branch? And
Sir,
from
few of them are from different branches, but majority of them are from mechanical background.
From mechanical background. And how many of the faculty members who are joining for the session or the training program are from the design background, or they have actually used the software or kind of thing? No idea.
No idea, sir. That
it's very difficult. Yeah. But as such, as far as my discussion is concerned, it may be a little bit boring for those people who actually were not at all interested in software programming and utilization of the softwares. So I would be trying to justify the title, as well as I'll be trying to get into insight of the finite element analysis, meshing, selection of elements. So these are the topics which I'll be discussing. Introduction, need of computational methods, then discretization or meshing in finite element analysis, need of element type selection, different types of elements, which type of elements are to be used for what purpose, what are the degrees of freedom associated with each type of element, and so on. Followed by the numerical computation, the very important thing and significant part of any software, commercial software, is the black box, the thing which we are not able to see or visualize. The software is actually doing some processing, like it is allowing you to visualize, to have some environment where you can sketch something, whatever you are thinking in your mind, that you are sketching. Then that sketch is converted into a kind of model, virtual model, that is known as CAD model, and that CAD model is converted into some kind of meaningful information if we are giving or supplying additional information like material process properties. Then we are saying that how it is supported or connected, boundary conditions, and how it is loaded, like loading patterns and all. So when these type of informations are given to the CAD model or virtual model, it becomes a FE model, finite element model. And pre-processing and solving part, that post-processing part, are the actually features of any finite element software. So numerical in computation, that is one of the very significant aspect which I am thinking of right now in this session to introduce to you, because I think all of you are faculty members and you are teaching for so many years the similar subjects, CAD and finite element analysis, finite element method, optimization, and so on. So you may be well aware of the fact that the mathematical part is very important as far as the softwares are concerned, if you don't know into, if you don't go into the intricacy and detail of the mathematical formulation and the solution schemes, generally we are saying solvers. Then machine processing ANSYS workbench. I'll be trying to show you some of the global control methods and local mesh control methods. And finally, a little bit on meshing quality, because these are the important things. We know that finite element analysis is an approximate method. So when actually what happens that we are living in a world where we are surrounded by so many things, so many phenomena happening around us, and so many domains or areas of concern are there with us. We have to look at those things. It is to be focused on that. Though we are very powerful in thinking, our brain is having super computing facility available with us, but unfortunately we are not able to grasp the behavior of very complex things around us. It is an unfortunate event, though if we are making use of the software and computers which are made by human being itself, but for the sake of processing in terms of quality and quantity, quantifying the physical behavior, quantifying the identifying and quantifying the one parameters which are actually going to affect the functionality of the physical system of which we are going to study or analyze for the purpose of designing. Basically what happens, we don't make in one go any system. We have to simulate using computational methods, using computers. We have to simulate the behavior in advance. We have to predict, and then once we are confident enough of predicting the behavior in advance before actually going to manufacturing of or making prototypes at the drawing board level or at computer simulation level, we are able to decide what is actually to happen in future. So that is a very nice, very good idea of going for the simulation. This idea came into mind way back during the initial phase of the competition, when the computational methods established. The process of actually dividing or subdividing all the systems into the individual components, when actually you can understand the basic behavior, the root characteristics of the original system, and then identifying those features, then rebuilding the original system from those components which are separated out from the whole initial original system, and studying the behavior of a whole system in terms of its nature, in terms of its characteristics, its behavior, in which the engineers are interested actually, and the finite element method evolved that way. Now, what are the requirements of computational methods? Why do we need to go for applying computational methods? Because generally we see is that classical theories are available for simple structures, simple beam, simple plate, straight uniform cross section, bar, circular bar, or similar kind of simple elements or simple geometrical objects. But for complicated geometries, these analytical expressions are not not popular and not devised yet. So that's what happens.
Pardon me, sir. Pardon me, sir. Sorry to interrupt,
Please.
sir. The voice is not clear. There is some voice going away in between. So that think there is
Oh,
some problem with the voice also. So just
is it okay now?
yes, sir.
So you have kept my video off, right? Okay. No, no. Is it okay now? Please convince me immediately
Yes, sir.
whenever I am not
Voice is
audible. Please,
the
please.
voice is not
I
now.
think
Voice is somewhat not getting clear.
now.
So when you speak continuously, there is some voice which is going away in between.
Oh, let me check out for the speaker. I think it should. Yeah. Now I think it must be clear. Is it
Yes,
okay?
sir. If it will, yeah, if it will be not okay again, I'll tell you, sir. You can continue, sir.
Hello. Hello.
Yes, sir.
Hello.
Yes, sir. Yes, sir. You are audible.
Am I audible?
Yes, yes, you are audible, sir.
Hello.
Hello. Yes, sir.
Am I audible?
Yes, sir. You are audible. You are audible.
Okay.
હા બોલ.
So basically,
હારું ચાલ હું કરું છું 2 મિનિટ. આ પેલો એમાં બેઠો છું ને એટલે. GD. ઓકે.
hello. Am I audible?
Yes sir, you are audible.
Okay. So I was talking about the need of computational methods. What we do actually, whenever we are not able to have analytical methods available with us, then especially for the complex, very complex and real life situations, what we do that we try to discretize, we try to divide into some small segments, then write down the equations for those small segments which are known as elements or finite elements. The continuum is divided into number of elements. The process is actually similar to that of segmentation. Whenever we have a large structure or large system, we generally subdivide into small segments, and then we assign the task to individual segments. Similarly, we are looking at the physics governing laws. We are looking at the equations related to those governing laws, like laws of physics, and we write down the equations for each element or segment, and the equations are then reprojected onto the global platform to analyze the whole system by going through the assembly process. So while going through this process, what we do, we actually lose some kind of information in terms of geometry, in terms of computational accuracy, and so on. So that's why these numerical methods are approximate methods. They are not exact. They are not giving exact solution, but they are giving very close to the real behavior. So it is better to have something than nothing. So the important thing is, the second aspect is, we use those methods. We try to get results and try to compare with the experimental work. Once we are comfortable with capturing the experimental behavior, real behavior of the real components, objects, or systems, then we can try to match with our prediction or simulation results. And if we are very close to the results, then we can further refine and we go ahead for accepting the results available with the simulation. And similar kind of experiments, simulation experiments or virtual experiments can be performed for the similar type of objects and similar type of systems. So that's the beauty of numerical methods. And numerical methods are well implemented in computers. We can easily implement the numerical methods. That's why the evolution of so many softwares has been possible. Basically, we are aware of these numerical methods: finite element method, boundary element method, finite volume method, and finite difference method. Basically, boundary element method is a method generally applied for large domains, where you need to, for 3D type of problems, you need to discretize the surface one order less than the dimension you are working with. Like 3D problems need to be solved by discretizing the surface, 2D surface, and 2D problems can be solved by discretizing the 1D boundaries. That way, boundary element method is very efficient as such for acoustic problems, for fluid structure interface type of situations, where actually you can think of hull movement in the ocean, ship hull movement, then the interaction of waves, water waves with the hull, and similar kind of things you can analyze. So large domain, boundary element method is very efficient. Finite volume method is also a numerical method in which is generally used for computational fluid dynamics, CFDs, and they are very powerful as such, as far as the computational fluid dynamic problems are concerned. Flow problems like blower design, then a large size room air conditioning system design, or it can be HVAC or similar kind of systems, or you can think of boiler design and so on. Finite difference method is again another method where you are taking you may be knowing about that. Forward difference, central difference, and backward difference methods are well popular. They are used for solving our routine problems as such, and simple problems. But for very complicated problems in which we are concerned with complicated geometry as well as different types of materials and combination of different types of elements, 1D, 2D, and 3D altogether, can be combined together in a single assembly, or we can separate it out. So finite element method is very interesting and important, and it has proven in the industries. People are using widely. It is adopted and well proven method for even very critical components, for as aircraft components, for aerospace industries, even for automobiles and portable equipments, and many more to be listed. So when we are concerned with solving real life problem, we are more concerned with producing or manufacturing different varieties of products designing the products at a very rapid speed and dump the product or market dump the product into the market very quickly and getting rid of the competition, heavy competition which the usually industries are facing with the competitors. So to quickly make the design, analyze the products, and finally get the production drawings based on the analyzed parts and producing them. So if the product life cycle is reduced, then there are more chances of getting heavy product profit, and also the growth of the company can be enhanced using this type of facilities available with the industries. So generally finite element methods are widely used for the mechanical systems, for electromechanical systems, for you can think of coupled systems. You can have thermal and structural analysis, a combination of thermal and structural, both coupled analysis. You can also think of CFD. You can think of this. Even nowadays manufacturing processes are also modeled using finite element softwares. To solve complex mechanical problems, FEM is the best suited method as far as commercialization is concerned. And so many softwares are available, like ANSYS. You can think of Abacus, then COMSOL, Hypermesh. So many other softwares are also available, SolidWorks, and yeah, you can go on adding in the list, Inventor, Katia. It is also possible that with different material types, combination of different element types, these are possible to be implemented in the software environment. Now, to introduce our CAD model or our model into the development environment where we are going for discretization or meshing, we need to import the geometry. We or either create the geometry or import the geometry. Earlier, ANSYS was struggling with the geometrical part as such. We had to make in Pro Engineer. Earlier, it was Wildfire 2, and we had Inventor, Ideas, different softwares for modeling, and we had to import the IGES file within the environment of the ANSYS earlier. Nowadays, ANSYS has given design modeler and space claim, different graphics features are implemented, so it has become very powerful. So importing the geometry is the initial phase. Then geometry cleanup. If there are some problems associated with the while going for the geometry making or modeling, there are more chances that some of the curvatures, some of the intricate shapes are not properly imported into the environment, and also they are going to affect the end results while going for the simulation. So that geometry cleanup is done, then meshing is done, and finally pre-processing and solution. We are going for the solution process. Now, what exactly is the discretization process or meshing in finite element analysis? Actually, we are dividing a structure to multiple elements, and the behavior of an individual element that gives a good approximation of local behaviors. Local behaviors mostly in most of the problems we are concerned with stresses and strains, and this actually the local behavior is then reflected back to get the global assembly of those elements which are separated initially, and that gives a kind of reflection of actual behavior of the structure or real behavior or characteristics of the structure. when we discretize the components or parts or assemblies, we need to verify whether they are good, they are going to give good results. How can we analyze? How can we look at the results? How can we rely on the results? So it is better to have a quality check. So mesh quality, that is to be once we go for discretization, get the FE model available with us, then we have to check for the element, how elements are distributed, what exactly is the size of the lowest element and the largest smallest or largest element available with us. This is the facility available in the software. Manually we can go for only 2, 3, 4 or at the most 5 elements. As such, manual calculations are required as such for understanding the method, how to actually come to know about the process or whole method, how it is being implemented. But practically looking at the real life structures, the structures are divided or discretized into large number of elements and large number of nodes. So this many elements and nodes are hardly thought of during the manual calculations. Yeah, you can also compute, you can go for coding, making your own codes, and you can that way make simple programs to understand the philosophy. But softwares are giving you very nice features. So what is the meaning of good quality mesh? If the mesh quality criteria are satisfied, if the mesh is valid for the physics which we are going to study, like we are going to study thermal, we are going to analyze thermal problems, or we are going to analyze structural problems, or we are going to analyze electromagnetism and so on. So depending upon the type of physics, whether the mesh is supporting that particular phenomenon or that particular domain, then if we are not getting good quality mesh, then we will be having some problems. One important aspect is the convergence difficulty. Actually, what does it mean? Convergence means when we run the simulation, we cannot get the results immediately. After prolonged period of time, the simulation goes on and on and on, and it doesn't turn up to the required solution. So there are chances of that non-convergence or divergence of the situation, divergence of the problem. That may be because of the faulty or bad quality mesh. So what we need to do is we have to check quality criteria and improve mesh. We have to think about model and solver settings before generating mesh. Perform mesh parametric study, mesh adaptation, and all. So different types of schemes are available which we'll be looking at. Then what exactly is the impact of mesh quality on the solution? The slide shows an example of when we are not properly justifying the quality criteria of the element mesh, then there are chances of accumulation of stress, which may not be there actually, but maybe because of the faulty meshing process can end up in different directions which we never thought of. This is again another example where you can see that the bilinear material property, having the property given the mention here, the results maybe varying, or the results may not be actually replicating the real life because of the faulty meshing procedure. Generally, what we get is the solution whenever we post process the results. When we go for solution and get the results, solutions are available at the nodes of the elements. Here you can see that here we have node of this is a tri-element, triangular. So we go for the solution and we take n1, n2 and n3, 1, 2, 3. Three nodes are there. So the value is averaged for the three nodal values. Generally, we get the values at the nodes, and within we'll see at a later stage that we'll have to go for shape functions for finding the value within the element itself. Generally, when we write the expressions, when we analyze the system mathematically, then we have to get the solution at the nodes that is known as the nodal solution. So nodal solutions are available, and if we take the average and we don't take the average, the difference between these two is actually for some of the problems on hand which I'm trying to show here, that turns out to be 19%. That means we have to think several times before analyzing the results, because mesh quality and how we are getting the results or interpreting that also affects our presumption. Now, what is the best element type for my analysis? Whenever I am going for the analysis of any problem on hand, how will I decide what type of element should I use? So the answer to this question is it really depends. Generally, we say haphazardly or in in vague way, we say that it depends, and really it depends upon the analyzer or the designer who is deciding upon the analysis type. Which type of analysis we are going to perform? What is the component on hand? How are we going to get the results? What are the parameters in which we are interested? Like our goal of for going for the analysis, particular type of analysis may be to extract displacements, sometimes temperature for thermal problems, mode shapes, natural frequencies, damping, and so on for dynamic problems, nominal strength, fatigue life, etc. for and stresses for from FSI problem. So depending upon our type of goal, what type of analysis we are going for, we have to decide accordingly. Then what are the shapes of the parts or assembly we are going to analyze? Varieties of components are available, and as because of the development taking place, lot of development advancements are we can see around. Because of the computational facilities available, because of the advancements or development in that hardware part also, enterprise or throughout the world, we can communicate in no time, almost in no time. So because of these things, we are ending up in a very complex situations, and many times we intentionally or somehow to show something that we are doing differently, we try to come up with complex problems or complex situations and complex shapes. So these are the challenges as such. And even for sometimes people are for optimization purpose, people are reducing the shapes, geometrical shapes and sizes. They are changing, altering the shapes such that the minimum material is consumed and manufacturing cost is minimized and so on. So these type of situations are leading us to go for complicated problems, complex shapes, and a combination of very complex or complicated shapes as such as assembly. So the important aspect is another important aspect I would like to focus on is the linear and non-linear problems, static and dynamic problems, and time domain and frequency domain problems. So we can have varieties of problems on hand. Generally, we start with any software. What we do, we go for linear static analysis only. But in real life, we know that everywhere the dynamics role plays the role, and with time varying loads are there, time behavior is there. So we have to capture the behaviors, we have to simulate the behaviors, and we have to identify those parameters which are actually governing the dynamic behavior. So it is a very challenging task for the analyzer or for the designer to make use of different element types as well as the element as an as a group of elements, meshing, quality of mesh. As far as ANSYS is concerned, because I'm more concerned with ANSYS and NX, Abacus, and Hypermesh, I tried to show you some of the elements here listed. Around 166 elements are there in the library. So which element is to be used when, how, why? So that creates a kind of puzzle within the designer. Basically, we are going for 2D, 3D solid and shell elements, 3D shell elements, then line elements. Line elements are generally used for truss or trusses and for 1D beams. So these are the some of the shapes and commercial names given to the linear and quadratic elements. And you can see that linear elements, we have end-to-end nodes at the endpoints of the edges of the element. Nodes are there, and here in quadratic you have one intermediate node available with you. So this is actually giving a provision of curvature adjustment within the body. These are general finite element types, and a few I have tried to show you as real components or real parts or systems, and they are converted into FE modeling. This is actually about 1D, 2-noded and 3-noded 1D element. These are 2D elements where we have a triangle, 3-noded, 6-noded triangle, intermediate nodes are also there. Then quad elements, quadratic generally say quadratic element, quad elements or quadrilaterals. These are shapes. Generally, because we know that the CAD model is a geometrical model, we are making converting the geometry on hand into CAD virtual models, and those models are then subdivided. So obviously, we have to take care of or equivalent geometry. We have to divide into this or discretize into number of elements, large number of elements, and the shape of those elements are decided based on the element, based on the actual component on which you are going to analyze. Here we have for 1D problems, obviously one-dimensional elements are sufficient, and they are easily they can be used very quickly. The solvers are giving results for 1D problems. 2D problems are generally employed where you have third dimension negligible as compared to the other 2 dimensions. And in 3-dimensional 3D problems, generally we are using tet elements, tet hex and tetrahedrons. Then we have this tetrahedron as 4 noded, and you can have 10 noded. Hex elements can be 8 noded, 20 noded, depending upon the implementation given in the software. You can have the commercial name is available here. You can look at the commercial name, and you can go to the element library within the help of ANSYS APDL help. Look at the library and see which kind of element is supporting which degrees of freedom. That you will have to look at. Then criteria for element selection based on analysis type. Quad or hex elements are preferred actually in case where we are going for crash analysis, structural analysis, and non-linear analysis and CFD. Tri or tetra elements are also preferred sometimes in mold flow analysis, wherever we are going for the casting simulation or forging simulation and similar kind of simulations where you have some kind of flow of semi-liquids. Based on project time, of course, it is very significant for the industries. Though for those people who are teaching at the institutes like me and you people, it is not that important. Time means not that important or constraint. Sometimes just you need to capture the behavior, you need to analyze and get confidence and go ahead. But in the industries, they have to have some deadlines to be followed. They want to get profits, they want to get their products manufactured quickly, and they want to capture the markets quickly. So time is also very significant sometimes, and where we are talking about millions of elements and nodes, this is very significant. That it depends also upon the large number of degrees of freedom which we are assigning through the modeling or through the discretization process. Quad and hex elements are preferred when there is sufficient time to generate mesh. You are having sufficient time, you can think of the solution process to take longer, and you are allowing those solution times, then it is better to go for quad and hex, because they are better, they are giving good results. But if you don't have enough time, then deadlines are very tight, then you can go for triangular and tetra elements. So these are the very important and kind of thing which we can think of while going for the comparison of one element type with the other, and try to go for the simulation process and get the time, compare the time taken by this software for the solution of particular problem. And sometimes what happens when we see the curvatures, large structures having very delicate shapes, if you accommodate, so using linear elements, it is very difficult to exactly follow the geometry of the complicated shape components. So it is better to go for higher order curved elements or higher order elements where you have intermediate nodes also. These intermediate nodes are actually giving the shape of the. If you don't consider this, then you will have lines to line segments, and you go on adding the intermediate nodes that gives a smooth curve. So that actually when to go for this, and whether you are going for particular type of element at some point of time, and you find that the computation time increases, and you know that you don't need to go for this type of higher order elements, then avoid going for those. Because when you go for convergence study gives you the saturation of a number of elements. Like you go on increasing the number of elements, the results are same. So the convergence criteria or the convergence study will give you that you don't have to go for large number of elements sometimes, and even for lower order elements, if you are choosing, you are getting better results as compared to higher order sometimes, because you are spending computational time in solving such type of problems where you are having stringent or strict deadlines. Quadrilateral elements are preferred over triangular elements, particularly for well-shaped geometry. For very large strain problems, using triangles can prevent element distortion. Actually, we will see these things also. Two phenomena I'll be talking about. The elements should not get distorted or deformed, because they will have to actually take up the load and pass on to the next element without actually getting deformed. So localized deformation should not be there as such of the element. You need to think of avoiding high aspect ratio. Aspect ratio is something, actually the ratio of length to width of the element. That should not be very high. And sometimes for shell elements, so we have to think of gradient. Actually, gradient is nothing but the slope of the element. At any point, really, whenever we are talking about the elements, and when we see that different elements, 2D and 3D elements are available, at each node we have degrees of freedom. For 3D spar elements, spar actually it has got pin like spherical joints, our shoulder joint and our knee joint type of thing, where we have 3 degrees of freedom, ux, uy, uz, and you look at this 2D or axisymmetric solid element, 2D element, where you have 2-dimensional provision of displacements ux, uy, and so on. So different types of elements have got different degrees of freedom, and actually the type of element which you are choosing, that decides the number of active degrees of freedom. Actually, number of active degrees of freedom, what does it mean? So when we look at this beam and this 3D quad shell element, you see the numbers of degrees of freedom are 6 for each node. So when you say for you are having a very complex in geometry and you are discretizing such that the large number of elements you are ending up with, so that is going to pose a problem of large number of degrees of freedoms you have to deal with, and the computation time will be increasing. So because these are actually active degrees of freedom, you cannot have any control. Once you use this type of elements, your number of degrees of freedom will be increasing, and that is actually increasing the size of the matrices which you are dealing with. You don't know actually when you will be compiling or you will be discretizing your component in your software, you will never know how many degrees of freedom you will be ending up, but the software has to take care of it, because it is actually on the at the background, it is making an assembly of large corresponding to the degree of freedom. The size of the matrix will be there, and that matrix is to be inverted, because we know that kx equal to f, and if you want to get x, we have to invert k inverse f, that will give you the displacement, and inverting k, that means you are inverting a large matrix, so it takes computational load on the computer, so processing time will be increasing. Generally, when we'll be using these two beam and shell elements, we have to sometimes locally we have to tune our mesh such that this the part or the segment of the component which is not required to have that type of beam or 3D shell element or 3D beam element. We have to avoid that, and that component, that part or that segment can be discretized with some other element. So that way you can reduce the number of degrees of freedom incorporated while going for the analysis. Then element shape function is actually, it is shape functions are the functions which are interpolating functions. We know that the nodal values are the values we from the solution, and if you want to get the values within the element, we need to go for some kind of elements. We have only corner or end nodes, and assume a linear variation of degree of freedom values within element. Sometimes we are attaching to 2D elements, we are attaching some more, for getting extra information, we are attaching extra nodes, and that that leads to the quadratic type of form. Linear equations are converted into quadratic by giving some extra nodes to the linear elements that can alter the behavior sometimes. But on these linear elements allow straight sides only, and curves are faceted. Quadratic or higher order more elements, that they are corner or end nodes and mid side nodes also. Of degree of freedoms within element and allow for modeling of curved boundaries. Generally, for complicated shapes having curvatures and very intricate shapes, quadratic or higher order elements are generally used. But to save the computation times, we have to go for linear elements by attaching for accommodating banding. We are attaching some extra shapes, and we can move element for our use, and that way we can minimize the computation time also. But not all the time computation time is important. Sometimes looking at the situation, the problem which we are taking on hand, whether we are compromising with the accuracy, or we are compromising with time. So important, two significant or important parameters, and many a times if you are having computational speed, by the component, how the component is getting deformed, and does the how this structure on your hand, structure or component or assembly is going to get deformed. That is actually the element we are used. These are the line bodies or lines, and actually they are used for girder structures, for the structures where you are having the third dimension. I would say z direction is very large, plane strain type of problems. Then you need to go for beam elements. It is better to go for beam elements, and you can control the property of the beam element by choosing parameter, that is key option, that is very important. You can
Sir, you are not audible. Sir, you are not audible.
on which your crane is moving. So obviously that should be a beam element, not the solid element. Yeah, solid element will give you result. Obviously, whenever you will be using software will always be giving you the output. But that output may or may not be correct. It may be faulty. Why it is correct, why it is not correct, that knowledge must be available with the analyzer or designer, and that comes only by actually applying or going through the analysis. You do the analysis, you perform the analysis, make a model, apply different types of elements, and then see the solution, see the so computation time, see the solution results, and refine, go on doing this. Unless and until you actually work on the software, you will never have a feel or realization of the process taking place within the software, because the mathematical part is also very significant. Choosing the beam element or shell element or solid element, you are looking at the type of phenomena like thermal or thermal analysis, static or dynamic problems, or you can have fluid problems, or a combination of different physics. So you can have a multi problem of element along with the mesh. Chord component is there, like you think of a pressure vessel, like you can think of the heat exchangers, boiler drum, and similar type of other practical problems you can think of, where you can think of the collapse of the system or collapse of the component which you are analyzing. We'll see. Let us go into a little bit detail of beam elements, how to select beam elements, and what exactly is the orientation of beam, how it is oriented in which direction you are interested to get the degree of freedom available, like the movement of beam will be in which direction, how it is loaded, whether it is getting twisted or bent, or it will be subjected to axial load or a combination. So depending upon the type of load acting, you have to choose accordingly. The beam element is not straight away, it can be applied for all the components which are slender or longer in length, right? So many criteria you have to think of. Actually look at the practical situation, how actual or real structure is going to behave under the influence of the loading pattern. What is the load pattern, whether it is going to get changed. Looking at everything, you have to think in advance, and then you have to decide the type of element to be chosen. These beam elements are very fast to solve. They follow beam theory. The computational data, the result data are very less because of lesser degree of freedom. Then forces and moments and linearized traces are directly available. Whenever we want forces and moments for any kind of component which we are dealing with, then it is better to go for beam elements. Or disadvantages are always associated with anything which we think in the other direction. If we say that there are some restrictions are there, so this cannot account for local stress concentrations. Generally what we think of, solid elements are giving better results as compared to beam elements as far as stress concentrations are concerned, and these are more difficult to define. Because of, as I said earlier, the 6 degrees of freedom are attached to each node, and if you are going for 3D element and you have higher order element, then degrees of freedoms are increasing. That's why it is very difficult to define as such. But when you go for manual calculations, you will have a difficulty. Otherwise, software takes care of these things. Yeah, some mathematical geometrical calculations are there which needs to be taken care of by the software itself. Then limited to constant or linear tapered cross sections. Generally, some kind of common errors we can encounter, we can come across while going for beam elements is a cross section. If
Excuse me, sir. Pathan, sir.
ના હું થઈ ગયો છું. હા ને ઓકે હા હું કરી દઉં છું.
દેખાય સર સ્ક્રીન.
Is it okay?
યસ સર સ્ક્રીન દેખાય છે.
Okay, done. So, actually, I have connected with the mobile itself. Both the things I am joining together. Now, am I audible? Clearly audible?
યસ સર.
Please
યસ.
let me know. Okay. So generally, when we go for higher order beams, which are recommended as such for the curved geometries, it is better to go for those type of elements which are supporting the geometry of the real life objects, than to tune the other elements, than to haphazardly or in a vague way you assume anything and assign any material, any element type to the geometry that may end up with bad results. Many times it happens. Now, unfortunately, in ANSYS Workbench, the new version they are coming up with, they are not allowing us to choose from different element libraries. That is possible with APDL only. And you have to go for ANSYS Mechanical APDL, then you have to go for that classic version, use that classic version, assign any material, any element type, and then you can come up with the mesh. Here in ANSYS Workbench, you have to have tuning in the parameters, generally parameters of the elements. So it is better to go for classic Workbench, use this APDL text, speed up your time, pre-processing time, because the problem with ANSYS classic is that we have to pre-process, and the preprocessor is not that comfortable or familiar. We are not we are not getting acquainted with the situation while using the working environment, when as far as ANSYS classic is concerned. But when you go for a Workbench, you have readily available the environment. All the things are drag and drop type of situations, tree view is also available, where you can pre-process very quickly, and visual icons are eye-catching, sometimes very easy to understand as compared to the previous, that classic version. I don't know how many of you have actually used classic, but please write down in chat box that we are those who are comfortable or familiar with classics, ANSYS classic earlier version APDL. How many of you have actually used text, this type of programming within the ANSYS software? And how many of you have used solid or shell elements? Which type of elements you are using? Please write down. At the end of the session, I'll be having some interaction. Now, shell elements, when you look at the shell elements, it has got 6 degrees of freedom. That is 3 translational and 3 rotational. All the degrees of freedom are supported by the shell elements within the solver. And the advantages are listed over here along with the limitations and disadvantages. It is faster to solve, no length to thickness requirements, less data created because of the thin geometry as compared to solid elements as such. Forces and moments easily obtained, and for those type of components which are collapsible, which are easily like vacuum chambers or surface condensers or heat exchangers, boiler drums, and as I told you, similar kind of structures where you have cavity. You are filling up like something, some fluids within or outside, and they are subjected to the loads. And we are interested in finding the forces and moments as far as structural analysis is concerned. These are very superior type of elements. Then they are difficult to define contact as such whenever we'll be dealing with shell elements. And the contact will come into picture only when you have some components are surrounded by the domain which you are considering. So when you have interaction of two different types of components, they are adjoining components. One is the shell and the other is solid. So to define contact is difficult, not impossible, but difficult. It takes too much time to define that. And defining the normal surface normals and connections is also difficult. When we say contact and connections, these are actually dealing with different components joined together, so that they are transforming energy or giving power force to one from one part to the other. They are coming in direct contact, like pin joints, and you look at the gears and you see belt and pulleys and all similar type of systems. Limitation and then some common error we have to focus on while going for using shell element. You can think of, you please take care of using shell elements. That the definition of normals that may be inconsistent, you have to correct while going for the quality check. You have to take care of the corrections. You have to make corrections by using different tools available in the software. Then line elements, generally this type of line segments are used for the structures, and like the structure towers having I as section, cross section, maybe H or W or any other section, girder section can be there. So you can go for line segments, and then you say that this line is having this cross section properties I, X, Y, Y, and moment of inertia, mass moment of inertia, area moment of inertia. When you are talking about motion, then mass moment of inertia comes into picture. Here you'll have to think of area moment of inertia then. So looking at the degrees of freedom supported by the line elements and where we are thinking of using it, then here look at the each node is having 6 degrees of freedom here. So shell elements, these are the actually commercial names available with NX. You can also think of NX, Nastran, and then there's Katia, Abacus, Ideas, Inventor, COMSOL, and so many other softwares where a finite element method is implemented for solving our problems. So they are supporting this. Each node is supporting the degrees of freedom because of the fact that we need not only translation, but we also need the rotation of that particular node under the influence of the external force we have to capture. Then solid elements are supporting only translatory degrees of freedom. So this is the problem many of the analysis analyzers or analysts are facing when they are using solid elements for all the type of structures, and they want to capture the rotational behavior. It is not possible because these are not supporting the degrees of freedom supported by the solid elements are only transitory. Now I'll be focusing on numerical solution. Very quickly I'll have to go for the rest of the things, like solution for the variables. Like once we go for this type of applying the meshing, this going for the choosing right type of element, we get meshing available with us. Then we will be looking at how are we actually getting or extracting the information from the software. So numerical computation is a part where actually for each element you have Gauss points. These 4 points are the Gaussian points, where we are actually finding out the these are also known as the integration point, Gaussian integration points, where we are actually calculating the values because of the fact that we are implementing the numerical method, and numerical methods are giving exact values very close to it without error or very less error at the points where we are capturing the information, and away from the rest of the domain the values are, because we are approximating using the shape function, the values will be differing. So numerical methods are implementing this way, that static analysis equation are evaluated like f equal to ku. So k is inverted, and you can always find out the nodal displacements, and nodal displacements will give you because you know the reference frame in initial position, you can always find the strain, and the strain values based on the material properties, you can find out the stresses. These are the things actually. But now look at the numerical integration Gaussian quadrature. Here is the function which we want to integrate, and -1 to 1 is the actually the limits of the natural coordinate zeta, which we are attaching with this element. The zeta for 1D element, it will be zeta. Here I'm showing you the 2D element, and I'll be showing you the 2D Gauss quadrature, where you have double integration, -1 to 1 for zeta and -1 to 1 again for eta. So zeta eta frame is attached to the 2D 2D element. Similarly, you can have zeta, eta, and xi for the 3D element. So this actually looking at the elements, how are we calculating? So at these highlighted points, we are capturing the values of stresses, and using the Gauss quadrature, this the functions which we are going to evaluate, they are not now polynomials, but they are approximated as they are approximated using different polynomials are converted into looking at the nodes, different nodal values. You get the sum of this and integrate. Integration is actually equivalent to summing up. By transforming using Jacobian. These Jacobian are the functions of the shape functions Ni, and these shape functions actually this we have some relationship between shape function and Jacobian, and these shape functions are related to the natural coordinate system, this natural coordinate zeta, and the weighting factor WP is actually applied to the in case of 1D problem. This is a 1D Gaussian quadrature Gauss integration process, numerical integration process, wherein the polynomial order P is 2np minus 1, where np is actually number of evaluation points. So by applying the weightage and evaluating for the equation, you can always get the integration done, and you can find out the stresses, strains and then stresses. For 2D Gauss quadrature also, here the table shows the zeta eta frame, which is the natural coordinate system. Now here why we are using Jacobian, that is actually a transformation, and here we will have a determinant of this Jacobian because we are going for the 2D case, and that's zeta eta frame is attached to the attached to each element. Actually, these elements are having some relation with the global coordinate system. So we have to have established the transformation between this natural coordinate system and the global coordinate system. Now, once we get at the Gaussian points, we get the values of stresses. We have to extrapolate to get at the nodal values, because the numerical method will give the values at the Gaussian points, which we are choosing actually, and extrapolation gives us the values at the nodal, gives the nodal solutions as such, nodal solutions or nodal stresses and strains, and that was for the linear elemental results. For non-linear results, what we do is we exactly copy this here. Instead of going for the extrapolation, we copy from the integration points. And this type of problems actually I encountered plasticity, the plastic deformation. Once you apply load and go beyond the point of deformation, then it becomes a case of plasticity. While going for using the finite elements, we come across some very crucial and critical type of effects. One such effect is a shear locking. Look at the figure here. We have two isolines, horizontal and vertical isolines, which are actually passing through these Gaussian points. And initially they are having some relation 90-degree angle between each other, vertical and horizontal. But when they are subjected to the some kind of load, they are deformed. Then the isolines in reality they should not be straight. They should get bent. And here look at the figure. This they are not following exactly 90-degree angle will not be there after the deformation as such. So this kind of behavior where the edges are unable to curve and leading to a change in angle at the position of the integration point, that is known as a shear locking. Here it should bend here. This is the situation we want, but this is happening. And in real life, it is not happening. It happens only in the software. So this is the effect is known as shear locking. And generally in FEA terms, shear locking causes the element to behave more stiff. What does it mean? Stiff means it actually moves as a rigid body, as if we are globally it is moved. It is not getting deformed as such, but globally it moves. And it happens only in linear elements because of the fact that the linear elements are not accompanying or they are not accommodating the curvature. Their edges are because the edges of higher order formulated element can curve, but these linear elements cannot curve. The other effect is hourglass effect. Here what happens generally when we go for 2D elements, and when we like I showed you here, I showed you 4 Gaussian points and the scheme of going for that calculation. These are the computation schemes. When you go for this, now what happens when you have a large number of elements in your structure and you go for calculation? This takes too much time. Sometimes you might have observed while going for the analysis that it takes too much time, like hours, or it can take days also. Sometimes, for depending upon the type of problem you are solving, it is very difficult to look at the solution quickly. And this problem will be there, especially for very sizable, relatively sizable problems. And to minimize the computation time, what we do is we reduce the number of Gaussian points. Instead of using 4, we go for only 1 point as such. If we do this, if we go for that, then what happens? Here we have 2 type of integration, reduced integration and full integration. What does it mean? Full integration, we are using 4 Gaussian points, and reduced means we are using only 1 to reduce the computation time. And while going for this, what happens actually, we are ending up with this type of hello. Hello. Any problem? Some disturbance is there.
Yes, sir. Just I will unmute that. Yes, sir. Please continue.
Okay, thank you. Thank you so much.
Yes, sir. Yes, sir.
So actually, that hourglass effect is nothing but a non-physical zero energy mode. Zero energy means hello. Am I audible? Hello. Hello. Am I audible? Modi sir?
Yes, yes, sir, you are audible.
Okay, okay, okay. Uh, Basically, what happens when we, as I told you, that RI is actually reduce integration, and FI is full integration. When you use all the Gaussian points, then the computation time is increasing. When we are having strict or stringent deadlines, then we have to minimize the computation time and we go for reduced integration scheme. This actually leads to hourglass phenomena. What is it actually? The phenomena says that here you can see the wrinkles. This type of situation comes across because of the fact that when you apply load, when you have reduced integration, then there are more chances of errors. The number of points exactly which you are capturing, the true values, the number of points, like four Gaussian points are capturing true values, and only 1 point is capturing true value. Which is better? Obviously 4. So when you are going for reduced value, then there are more chances of errors, and approximations is already there in the FEM, and you are introducing one more approximation of reducing number of Gaussian points. That leads to the zigzag pattern, and this is known as hourglass effect. This should not happen as such, and to overcome this, we are plotting the energy, hourglass energy, for different types of structures, and then meshing those structures and finding our hourglass effect. That feature is also available in modern softwares. You need to check out these things. Otherwise, what happens, the when you are this becomes a kind of situation where your elements are moving freely. There is no as such if a pure effect of the loading pattern which you are applying. Here the figure shows that you have, even though you have 4 Gaussian points, you can have shear locking. Shear locking can be possible because of though you have 4 number of Gaussian points, but you increase the number of Gaussian points through 9, you will not be facing any shear locking problems, and also you will not have any hourglass problem. So you have to sacrifice your computation time. Then I think I have 20 minutes more. I'll be about to complete my my discussion, and the important part actually I'll be going through now onwards. Meshing process in ANSYS. Generally, ANSYS mechanical. In ANSYS mechanical, you have meshing feature available as a tool. You directly you import the geometry, then you right click on the mesh, click on generate, and get the mesh generated. This is the default mesh which you will be able to generate. That may not be accurate, or that may not be correct mesh which you are interested in as such. And when you will be happy, yeah, I am getting the FE mesh generated very quickly in within the environment. I don't have to do anything. So you forget that part, because I am trying to give you some kind of things like global and local control, through which you can alter your mesh, and you need to go for that, because rest of the things are error prone, which researchers have proven. The mesh is actually representative of nodes and elements. Here through nodes the load is transferred, Mesh is comprising of number of elements. It can be 1D, 2D, 3D. Here we are looking at the 3D elements. We'll have here, if you are thinner section, you can think of shell element. But this has got sufficiently large dimensions in all the three directions. So it is better to go for solid element. Here triangular type of shape, that is a tet element, tetra. And if you see square or rectangular type of shape, that is hex element in case of 3D. Now our default mesh is automatically generated during a solution, and it is generally recommended that the additional controls be added to the default mesh before solving, because these are maybe maybe error prone. So we'll go through two types of mesh control, global and local. Let's have a look at the global mesh controls and their different parameters of the global mesh control. Actually, what is the governing physics actually which we are dealing with? The physics, maybe what does it mean? Physics means what is the type of problem we are solving? Are we going for the mechanical, like static problem, or the dynamic problem, or a combination of the thermal problem? So we can go for mechanical. So these broad categories are given by ANSYS, not universally adopted by everybody. But yeah, because we are dealing with ANSYS, right now I'm trying to talk on ANSYS meshing and quality mesh, and then it is better to think of that particular environment right now. So mechanical, electromagnetics, CFD explicit. Different analysis types define acceptable or favorable element types or shapes differently. And if you look at the relevance, that is a very important, significant criteria or parameter where this you can control the size. Look at the left hand side figure here, and middle and right hand side. Right hand side is the fine mesh, and left hand side is very coarse mesh. So depending upon the type of problem which you are taking on hand, and the accuracy level which you want, you can always go for sizing or resizing the element meshing. So relevance is a parameter which actually is set between minus 100 to 100, and its default value is 0 when we don't do anything to relevance parameter, which is here. I'll show. Yeah, this is the the middle value is 0, and at left hand side is minus 100. That is actually giving you coarse, and right hand side gives you fine mesh. The relevance center is between these two. So depending upon where actually you are setting up the midpoint of the relevance slider control, and that is available in ANSYS workbench. Element size defines the maximum element size used for the entire model. Maximum element size, your element can be smaller than that also, depending upon the situation where the algorithm has to decide within the geometry. What kind of geometry we are dealing with, we don't know right now. But when we look at a particular geometry, we can easily identify and locate the point or the place where we can have the element size smaller or larger, but the largest value can be controlled. For most static structural applications, default values for the remaining global controls are usually adequate. Now, additional control we are going to talk about over the global mesh. Actually, in global mesh, initially here, while going for relevance and this, by choosing this physics and then going for the relevance parameter, we could control the size of the element mesh. Then to go further into details and analyze the geometry and the meshing quality or type, then it is better to add some control over local control or maybe global control. But there must be a control over the meshing, the way we want meshing. I would say one important aspect over here that the HyperMesh is a very powerful software as far as meshing is concerned. ANSYS is very powerful for as because it is accommodating large number of solvers. The numerical methods are implemented and the solving algorithms. That means solvers are very powerful as far as ANSYS is concerned. But meshing for meshing, generally people are playing with the mesh using hypermesh. That has I had observed so many years back, 18 years back as such. When I went through some similar type of training program, not online but offline, and we had a practice over working with the modules. So it is very nice to play with the mesh. So playing with mesh means what? The area which we dislike, we change it, we alter it by our own. Like we are sketching on the paper or on the piece of paper or something like that. We do alter our mesh as per our requirement. That is actually the level of control they were giving in hypermesh alter incorporation. So additional control may include curvature, fixed proximity, and combination of proximity and curvature. And these are advanced size controls, especially used for advanced analysis types. And this analysis type are nothing but the nonlinear analysis, thermal analysis, transient analysis, and also you can think of rotodynamics analysis and so on. So very complex type of analysis can be dealt with advanced size controls. Here we are looking at the fixed curvature, both these two, fixed and curvature type of size control. These are available in sizing tool. If when you go for meshing, I think I expect and I think that I hope that after my session gets over and when you will be going, whenever you will be going for using ANSYS next time, you will always be remembering this detailing which I am trying to show you. My interest is basically to give an exposure of the features which are available in very powerful tools. We are very lucky and we are we are living in an era where actually we have got lot of information available. We have got sophisticated tools available on our table, and we are not using them properly. It is an unfortunate event as such. But when you will be able to have by wearing the different sizes, element qualities, changing the qualities of mesh and changing the element types, you can publish so many papers using varieties of simulations and concluding or interpreting the results. There are a lot of opportunities for you people to work on, because you don't have to code as such. Because earlier people, Bezier and all, they were coding their Bezier cows, their cows. It was like kind of situation where we are having enough of material available with us, and so many things are moving around. So only just you look at this feature, you have on curvature, so you just select and you just look at the the effect of changing the degree, 20 degree and 75 degrees. So when you say curvature, that very smooth curve can be obtained by the value of curvature to be lesser. So by altering the meshing, by using the tool properly, you can always get better quality mesh. Advanced size control has got one more feature as proximity. Proximity, its name implies that it is close to something. Like here, look at this gap between these two, boundary and this pin type of object part. The gap is something in which if we give number of cells to be 4, there are 4 segments here in between. But when you increase the size, it gives you more number of cells. That means for the stress concentration problems and for some type of problems where you have to have heat transfer identification of the effect of thermal effects of various domains or cavities and system, that can be captured very easily using this feature. So proximity allows you to refine the mesh at this situation where you need to have a large number of elements as such. When you have lesser number of elements, you will be ending up with faulty results, and that is obvious because of the fact that these continuities are always giving you stress concentrations. Then looking at the local meshing controls, local mesh controls can be applied to either a geometry selection or named selection. We can have two options available in ANSYS. There are different controls: method, sizing, context sizing, refinement, mapping, matching, pinching, and inflation. These are the tools which are available, readily available in the software, and you can always make use of these softwares as per your requirement. Not always needed, but yes, when you know this type of things are there and you just start working, it is not that difficult. Only just clicking this method and go look at this readout, then apply one by one. You apply and you check out for your model. That will be, I am just trying to you people to give a kind of idea and initiation can be what I would say is I wanted you people to get initiated. Get initiated with the tools which are available with us. We are not as such making use of these things. We are just using for solving simple problems. For complicated problems we get stuck up, but why we get stuck up? Because of these things which are available but we are not aware of it. Now method control, here we talk about the method: sizing, context sizing, refinement, mapping, matching, pinching, and inflating. These are the local mesh controls. And I'll be talking about a little of 2-3 methods. Method control provides the user with options as to how bodies are meshed. How are we going to mesh the object? Here method is option. When you don't do anything, by default it is automatic. By default it is automatic. Hello. Sorry, I was about to receive a call. I didn't receive. Am I audible?
Yes,
Sorry.
sir. Yes, sir. You're audible. Yes, sir.
Yeah. I can't put my mobile on a flight mode because I am speaking. I am using it for this session. Unfortunately, automatic is the default case where body will be swept if possible. Otherwise, the patch confirming measure that is under that tetrahedron. The tetrahedron option is available. That will be initiated automatically by default. And when you have the different types of meshing methods for 3D bodies are available, like automatic, which I showed here by using this automatic tool. Then you can have tetrahedrons, patch confirming and patch independent. We'll see these things in a very short while from now. Then multi-zone, hex, dominant, sweep. These are the methods for 3D. And for 2D, we have automatic method, quad, dominant. Then triangles and uniform quad or triangles, uniform quad. These are the actually types of elements which are implemented as a method, and these methods are nothing but the algorithms implemented in the software for 3D and 2D mesh elements. Tetrahedrons method. When you apply tetrahedron, obviously you can see these tet elements are chosen by the software, but the quality of this can be varying depending upon the option which you are choosing. Look at this right hand side which I am highlighting. You can have different patch conforming, So you will be having this mesh, then underlying geometry. It is accommodating the geometry. Looking at the geometry, and here you don't have anything, so it is a face straight away. Here also you have a curved surface, but you don't have any element as such. Here you have patch confirming. The patch means surface patch that is confirmed, and that tool gives you a kind of mesh. Then patch independent. So depending upon different types of features available, you can get you can get different types of meshing, and also you can verify your results with different meshing and compare the results which mesh is better for your particular problem, and the how closely it is matching with the experimental work. So for research purpose also, that can be very fruitful and informative. Whenever you'll be presenting your research progress committee, they will also be appreciating you people that you are going into details of this important aspects. These are actually physics and mathematics, the mathematical aspects being discussed in light of the commercially implemented software. Another method is hex dominant method. Here also you look at this only, select this method and you will be able to create hex dominant mesh. You can see the difference between these two mesh. Here you have hex element, hexagonal hexahedron as such, 3D hexahedron. When you have 2D, you can say actually quadrilateral. So here look at this triangular type of shape, but these are tetrahedrons. Here we have hexahedrons. Why hexa? Because you have total how many? Here you have tetra. You have 4 faces, 4 nodes. Here you have 6 faces, 6 nodes. Now, this hex dominant method is recommended for meshing bodies with larger interior volumes. These are not recommended for thin or highly complex shapes, but sometimes people are using for complex shapes. They are ending up with bad results. When they try to compare with the results of the others, other researchers or experimental results, they deviate a lot and they end up with some high errors. So it is important to think and choose appropriate type of element, and meshing type of is also very significant as such. Not only type of element, but also how these elements are joined together to form a mesh. And this is useful for meshing bodies that cannot be swept. Sweeping is something like you are moving along a trajectory which can be a 3D or 2D. You are moving across the that geometry, and sometimes some intricate shapes are not allowing you because because of the merging of the geometry or material at some parts. So in that situation, this hex dominant method is useful. Here is the sweep method. You have source and you have target, and you just have this type of objects. You just select these two. Automatically, you will be able to get this sweep method give you the sweeping of the elements, and meshing will be done. Then multi-zone sizing. You can have tetra, hex dominant, hexa dominant, and hexa core. So you have, this is your geometry, and you can freely control unstructured mesh type. These are different types of meshes which you can get. So you can also refine as such by changing the size of the size of the elements. Then surface body. These are different meshes. Sometimes you go for very fine mesh, but this fine mesh may not be may not be useful. The results are very close to the coarse mesh itself. So it is better to go for coarse instead of going for fine mesh. So this type of things can be available only by having hands-on practice and by going through the personal experience. You can come to know about whether we should follow this method or not. Then you have surface body quadrilateral dominant. That is by default quad elements will be accepted, and it is attempting to match with as many quad elements as possible, and it fills in with triangles wherever you have space available with you. Because the quad elements are not right rectangulars, right? So you can have some type of space available with you that will be filled up with triangular elements, and all triangular shapes are used where when triangles are selected for surface body method, and multi-zone quad tri or elements can be used depending on settings, or quad or tri shapes are created using a patch independent algorithm, as I explained here. Patch independent combination of both the types of elements, or many other, maybe because on the surface we can't see. If we take a cut section, then from within the body you can have different types of element accommodated, and that is only because of the algorithm which the solver is implementing. We never know about those algorithms, but we should at least know about the functionality, how we are able to get these different results by actually going through the process. One very important and significant feature is the sphere of influence. When you apply, when you put up a center somewhere and you give a sphere size, then you will be able to get the mesh within that domain which is touching the surface. The sphere which does the intersection, common intersection surface will be meshed that way. That is the actually local size control over meshing, and all scoped entities within the sphere are affected by size settings, and only the portion of the scope face or body within the sphere is included in the scope of the mesh control. Not the rest of the part is affected, because that many elements will be altered when you go for the sphere of influence. Here, look at this. You have this option available, sphere of influence. Now, I'm about to conclude. Please bear with me for some 5 minutes. I think I'm running out of time. Maybe because I started a little late. Then context sizing. Whenever we are dealing with the problem somewhere where you have junction of two different
Bye.